Hi, everybody. Thank you for joining us today for the CHIPS biannual tech update. It's great to see everyone here, and thanks to Google for providing us a beautiful location here in San Francisco. I really appreciate that, and thanks all for coming in person. And then also for all of us, all those joining us online, I apologize for the logistical challenges that always seem to come with any event or any meeting. So anyway, but that just seems to be par for the course no matter what. But again, thank you very much. So, just provide a couple introductory comments. We had some great talks this morning, and I look forward to hearing them. But really what CHIPS Alliance is all about, and what Linux Foundation more broadly is about, it's about collaboration, right? It's about different folks, different teams, different companies working together on hard problems. And the belief that by having a community or building a community to collaborate on these hard problems, that's how the best innovation comes forward. That's how these problems are tackled. If you particularly look at the advancements that have occurred in artificial intelligence, really in a very short time, I mean, of course, it's a very long history in that overall technical area, going back into what I think the early 60s or late 1950s with some of the work from MIT, right? But irrespective, it's been a long road, but it's really starting to accelerate now, and that's in large part because of the amount of collaboration, right? So at least in terms of Linux Foundation, what we sponsor, right, we're up to like 18,000 developers, and that's been in the past couple of years. So that's really rather remarkable. We're trying to do that in chip design, right? And it's a long journey, and there's obviously different constraints in the chip world compared to AI, but there are also similar concerns, right? And a lot of that boils down to security or proprietary data, right? And how to handle that and treat that, right? So that's something that, we continue to look at relative to chips. But again, for all of this, it really boils down to collaboration and participation by different companies and organizations to help make this go forward, and really to build up a trusted source of IP catalog. And that IP could be, actually RTL, it could be firmware, it could be EDA, et cetera, right? But building that confidence so that, if you're part of a company or university, when you pull a piece of RTL or something from our repository as an example, that it's good, right? That it's going to work for you. But if there's a problem though, too, we certainly always welcome contributions back to that as well. And that's overall part of building that community. Whoops. So, we've been fortunate, we've been gaining some members over the past 6 months or 8 months that we've joined. So it's great to have AMD part of us, Microsoft, NVIDIA, Marvell, amongst others, Axato, who've joined us. And so we welcome them, and particularly in participation on the Root of Trust project, Calyptra, which we'll be hearing more about later today. So look forward to hearing about that. And again, as I've already said this really in so many words, but really we're about open collaboration across the entire spectrum of building chip design. So with that, I will stop chatting, and I will introduce our first speaker, which I am very pleased to announce, and that's Michael Gilda from Antmicro. So Michael is a VP of business development at Antmicro, and also a great enthusiast and sponsor and supporter of CHIPS Alliance, as is his brother Peter, who is also here with us, and thank them as well for all their help and contributions to open source. So Michael.
Hey everyone, just give me a second. I need to connect to this event and show the presentation. I hope so. Seems so, yeah. Okay, I think I can do this with the screen, right? Change layouts. Spotlight. No. Mirror both screens. Great. Let me see if I can change the slides easily. All right, good. Welcome. It's a pleasure to be here, and great to have everyone attending virtual as well. So today I'm going to talk about Calyptra and Veer and all the work we're doing. This is all enabled by CHIPS Alliance. It's really taking a lot of prior great work and putting it into practice in a collaborative project. So I think that's exactly what CHIPS Alliance is about. A few words about us and why we're kind of doing this. So we're kind of working with commercial adoption of open source, trying to make it useful in practical scenarios. And we're a engineering service company, helping people to build things. Very often we find ourselves work with tooling, and specifically we work a lot with ASIC and FPGA-oriented tooling, as well as IP development, all sorts of open source tasks that help people build practical things. And of course, like, you can't do it well without software, without automation, without CI, and that's a major focus. Veer, that we're going to be talking about today, is a family of 32-bit open source RISC-V CPU cores. It comes in 3 options. They're all hosted by Chips Alliance, so these links here in the slides, we'll share the slides, of course, as well. They all point to a different version of the same thing. So today, specifically, we'll be talking more about the EL2, the kind of core that's embedded inside the Calyptra root of trust. But of course, you're free to explore the entire family, of course, and use it for your own designs. This is ASIC-proven RTL. These are pretty mature cores. They're implemented in System Verilog. And yeah, right now we're kind of giving them a new life, maintaining them, adding features, making sure they work, using continuous integration. Calyptra, if you are not familiar with the project, it's an open source root of trust. It's specifically meant to be integrated into other solutions, so bigger SoCs that need a root of trust functionality. The idea comes from collaboration in OCP, Open Compute Project, where 4 big players, NVIDIA, Google, AMD, and Microsoft, got together, and they have the same problem. They need a root of trust, so that if they're buying hardware or developing hardware for their servers, they can actually rely on the security of those blocks to be, well, uniform, unanimous, comparable. They can reason about the security of those building blocks in a similar way without having to test and debug, 12 different solutions to the same problem. So it's meant to, and again, it kind of is really well tied into the mission of Chips, which is standardizing, which is making people reuse RTL and tools instead of kind of reinventing the wheel. And it kind of is a great example of a collaborative project, because since it started with those 4 companies, and of course by now we have like probably a dozen others collaborating, obviously we need to find ways to work together and processes to make that collaboration efficient. So overall, the mission of Chips here is to host the implementation. So the spec is kind of hosted in OCP, but the actual implementation and all the technical work is going on in Chips Alliance. All the repos are kind of found under the Chips Alliance GitHub organization. And it's a Paragon project, where we're kind of helping establish methodologies to collaborate on open source RTL. Calyptra itself is kind of, at least the 1.0 version of it, is focused on very specific features. We're not trying to kind of boil the ocean, but more like specifically address the need as it is today. And there are plans to integrate that first version into real products in the near future. As I said before, it uses the Veer EL2 core. And of course, it has more than just a core, right? It has a bunch of different peripherals. Many of these are actually reusing, OpenTitans peripherals. Again, we're not trying to reinvent the wheel. Whatever great open source building blocks we can find, we try to adapt to our use case. But of course, then we're doing some things differently, right? So that's why the Calyptra project was kind of born. Now, our work here is specifically focusing, so when I say now I mean Ant Micro, it focuses on making it a collaborative project a little bit more. And collaboration is best done with open source that can be fully reproduced and easily scaled. And the main goal is, to introduce better testing and more coverage and public-facing CI, all sorts of things that, of course, you can do with proprietary tools, and people do that a lot, but the challenge is that it's kind of hard to share that methodology easily, to make it completely reproducible for other people. For new partners joining the project, how do you actually get them on board quickly, and how do you make it easy for them to reproduce your results, right? So open source is a good answer to this. And certainly, we're not meaning to like replace every existing tool out there, but more like augment existing workflows that each and every of those companies, so Microsoft, Google, AMD, NVIDIA, have internally, right? Internally, they have, of course, their own huge flows and tools and everything. But we're trying to kind of add an open source layer of great stuff on top of that, which would enable us to have smoke tests and the ability to reason about the quality of the code and lint it and so on. So basically, that's the focus of this project, and we're kind of executing on this project. So let's start with all the things that we've done, starting with Variable. Variable is a tool that was donated by Google into Chips Alliance. It is being developed within Chips Alliance. We're pretty involved in the Variable development itself, and what it does, it's a system Verilog parser and toolkit for linting, formatting, and also includes like a lexical diff, obfuscator, and indexer. And from interesting things, it also has a language server. So it's a pretty versatile framework for working with system Verilog code, and it's completely open source. It's under active development. It's pretty widely used. It's a great tool. So yeah, we actually had some questions yesterday about, is open source linting possible? And the answer is yes, absolutely. It's not even the only tool that can do it in the open source space, but certainly it's one of the major ones and one of the more actively developed. As I said, it also includes a language server, which is kind of makes it even more useful because it integrates very well with a variety of editors. So whatever tool you're using for editing your code, you can actually integrate through this LSP layer. There's documentation that tells you how to do that, and we support most of the features that are possible with language servers, including auto expansion. There's also a blog note that we wrote about this specific feature, so feel free to read it for more background. There's also a plugin for VS Code. We were aware that VS Code is kind of becoming the de facto standard for IDEs. So to make things easy for people, there's an official plugin. We had to go through, like registering our official account in the VS Code extension marketplace and so on and so on. But we have an officially supported plugins. There's, of course, other ones, but this one is the ones that's being maintained by Chips Alliance. From interesting things with Variable, we also have GitHub Actions, which make it super easy to integrate with existing code bases on GitHub. I believe it's pretty awesome because you can get feedback on your pull requests. You can get linting suggestions or even kind of formatting real changes to your code that you can just accept, right? So you kind of submit a PR and it sees that, okay, this change is not really great. Perhaps you could do it differently. So it's a personal assistant for your code. Very cool. I advise you to check it out if you use GitHub Actions at all. There's links to the specific actions, and integrating them is just a few lines of code. Yeah, I believe that. Okay. So kind of that's the Variable part. As you can see, there's quite a lot of stuff out there. Moving on to the next topic, we also have a lot of work around testing that we're doing. And as you know, of course, testing and verification with open source tools is certainly possible, but then not necessarily the industry standard way to do it. And Veer is kind of an example where originally the testing methodology for Veer being based on closed source tools, upon open source release of the core, not all of it was released, right? So the core was verified by the original authors to a very kind of deep extent, given that it was shipped in like millions or perhaps even billions of devices. But the actual test benches, could not be fully released. So we only had system level tests to start with. So basically, one of our goals is to kind of increase the coverage that we started out with, and we've been adding this as like public CI checks, so that if there's any changes to the core, we continue to test against all those scenarios. And of course, we generate a report with coverage, and there's a summary web page with links to more specific details and so on. There's a link in this presentation as well. And now, naturally, kind of taking it to next level, we want to make sure that things continue to work. So One of the ideas that we have, given that all of the organizations involved in Calyptra are actually active users of UVM long term, and it's a goal of CHIPS Alliance that precedes this project, but I think like this project kind of shows that it's necessary, is to add UVM support to Verilator, which is a difficult task. Everyone admits it's hard. But on the other hand, we've had quite a lot of success, and we've covered a lot of ground since we started. Originally, Western Digital was a big kind of sponsor of this effort. Nowadays, it's kind of the funding's coming from different sources, but generally speaking, we're pretty close to parsing the entire UVM library with Verilator, as well as, of course, we'll need a few more features to actually go and do proper UVM, large-scale testing. So definitely, if you have need for this, you're invited to kind of talk to us and kind of figure out a way to accelerate this work, because we know from many sources it would be really, really great to get it past the finish line. So far we can't do this. Unfortunately, we can't, do actual, UVM end-to-end. But also we believe it's possible, and it's not extremely far away. On the other hand, of course, there's open source methodologies that people might be aware of, CocoaDB, PyUVM being two of them. PyUVM is actually a Siemens tool. CocoaDB is a community-driven FOSSI Foundation-backed project. They work together. You can use them to test things in a UVM-like methodology. So if you're not afraid of Python, it's a great way to do your stuff, and especially if you want to keep to something that's like familiar, PyUVM would be a way. CocoaDB is more generic. You can of course do CocoaDB testing without PyUVM, and you can trust the developers that consistently rate CocoaDB as an excellent tool that does a great job. But we're also aware that a lot of the world's developers in the verification space, they're just used to System Verilog, they're used to UVM. So we'll have to tackle all these ways of testing in parallel, right? And eventually we want to be able to do this. But in case you want to do open source testing and verification today, there is a way. And there are also examples in the Vir and Calyptra repos how to do this. One other interesting thing that we added, it's still kind of experimental, but I think very, very useful. We do run the entire Vir core through the open source RTL to GDS flow with OpenRoad. And this is part of the CI. I mean, it's a work in progress PR, but it's kind of working now. So we just need to clean it up and merge it. Now, this allows us to do like this smoke test where any changes to the RTL, like we can certainly see if they compile, if you can synthesize the real design. And as we all know, OpenRoad, of course, is still in its early days, and you won't get the same quality of results as with other tools. But at the same time, it has a very interesting quality of being possible to run, perhaps with AI on 1,000 computers, or you can experiment with different parts of the tool chain and, do research on top of it. And even if you get worse results, you might just get them quicker compared to other tools. So overall, we believe that having OpenRoad support here is important. We would want to extend it to cover all of Calyptra in the future. We haven't done it yet. And also one other limitation so far is that normally, if you want to run things through the OpenRoad flow, by default, it'll support some System Verilog, but not enough to cover your real designs. So one of the ongoing projects within CHIPS Alliance is also Surelog UHDM and a related Yosys plugin, where we can actually parse a very significant part of the System Verilog spec. And in fact, we're not far away from parsing all of Vir and Calyptra in general. So there's ongoing work to just enable this. We can parse OpenTitan, we can parse Black Parrot, right? So you can kind of run very serious designs through this plugin already. And it's just a matter of time before we can kind of run Calyptra too. And that will, of course, enable us to just compile the entire design without having to have SV2V in the middle. Okay, so moving on to another way of improving, the verification of the core. There's a framework called RISC-V, which is originating from Google, but also now donated into CHIPS Alliance. And this is an open source framework for instruction set generation and testing, of course, comparing, generating random streams of data and trying to see if the implementation is behaving correctly as compared to instruction set simulator. So we had to add a bunch of things to make it work with the current code base, but it wasn't extremely hard. One other interesting piece of work we managed to do in the last few months is improving the Python-based generator in RISC-V. So RISC-V itself is kind of based on UVM for the instruction generation part. And that means, of course, if you were listening to what I was saying earlier, we can't do that with open source yet. It's something we'd like to do. So if you're interested in this, again, talk to us. We'll eventually get to do this, but for now we're kind of limited to different approaches. And one of the other approaches that RISC-V also has experimental support for is completely bypassing the system Verilog part and using Python instead. And we kind of extended and improved this Python implementation to actually work. It's still not like on par in terms of features with the system Verilog version, but nevertheless, it's kind of good enough to do some level of testing, and we can run it completely publicly, completely open source, which I believe is pretty cool. And we know that there's interest in kind of extending this to cover, all of RISC-V in the future, which we'd also like to do. Another thing, like from the technical work that's gone into the project recently, and that part will kind of grow. So right now we'll probably be kind of extending the project to also cover some additions and extensions to the core itself. So now that we have some methodologies to test it better and a framework to kind of run CI and so on, we can start adding features without the fear of making things explode. So one of the problems we had was that we needed a JTAG, and Calyptra adds this JTAG interface, and we created some testing to make sure that the JTAG interface actually works. Again, open source, it can run in CI. And we actually found a problem, right? So we kind of found that you couldn't access a peripheral from the debug interface, and Calyptra just didn't connect the bus in a certain way. It was kind of a simple and stupid bug, but certainly kind of proves that this testing is needed, because it felt like a very obvious addition, right? A small change, but actually it wasn't fully correct. So that's why we need this entire infrastructure here. And now we have tests to, of course, see that this bit is working fine. So going towards the end of the presentation, one of the things that was also pretty central to the project is trying to figure out, okay, how to actually make this scale, how to make it collaborative. And as you know, in the ASIC space, many of the workloads are not trivial. They're not something you can just run in 5 minutes. They might take hours to complete and require a lot of memory and a lot of compute power. So one of the projects that we've been working on in CHIPS Alliance for years now is so-called custom GitHub runners. And those custom GitHub runners are effectively a technology that allows you to, instead of the default runners that you get with GitHub, instead you run your own machine. We're using GCP for this, obviously, because it's a collaboration with Google. And this allows us to pretty much scale up to whatever kind of machine we want and however many resources we require. Run lots of things in parallel without fear of running out of resources and stalling everything. And we're kind of using it in a bunch of projects. This is not the only project using those runners, but specifically for Calyptra, one of the things we're working on, we already blazed this trail, but here it's going to be especially important, the ability to run proprietary tools on top of the open source stuff. So that we can do it without exposing secrets, without kind of causing any problems for everyone, but still we can get the support we need. We can kind of run the real flows that those companies are using in a secret and secure way, only exposing the results that we need to expose. So this is one of the ongoing tasks, partly because it's kind of hard to set it up. One of the problems that open source is trying to fix is that open source is really easy to set up. Like everything's just there, and you get the code and voila. But of course, this is hard to do, but we want to do this so that we can increase the confidence in the code. So the GitHub runners are a central technology here, and they're also open source. You can see this on GitHub. You can read a blog note about it. And if you have a similar need where you'd like to kind of scale up your CI especially for public projects on GitHub, right? that might be a good solution. One last thing I wanted to say is that the work is ongoing, so we'll probably have some more news by September. And in September, right at the beginning of Oktoberfest, so no suggestions there, but you can come to Munich and enjoy not only the beer, but also a really, really awesome conference. It's one of the greatest open source conferences out there. It definitely kind of groups a really interesting crowd. It's happening September 15th to 17th. It might be a little bit troublesome with hotels because of Oktoberfest, but we hope we'll manage. And yeah, we're certainly going to do a Calyptra talk there. And hopefully, of course, in September, some of the things I was talking about that are in progress might already be in place. So yeah, you're very kindly invited. If you're interested in these things, I'm sure that you'll find OurConf interesting. There's also an American version of OurConf called LatchUp that some of you might have attended, and this happened already this year, but I assume that next year there's going to be a new edition that you should definitely join too. All right, thanks for your attention. That's all I have. Do you have questions, perhaps? Or anyone from the online call? Okay.
Random question, because you mentioned some of the RISC-V cores that you're using were in System Verilog. Sheer curiosity, what made you guys choose System Verilog?
So I will repeat the question for everyone to hear. What made us choose core implemented in System Verilog? And it's a great question because we also host Chisel, right? And there are other kind of languages and methodologies to build RTL in these days. I guess System Verilog is just a conservative choice of, like all those big companies are huge System Verilog shops, including Google, including, NVIDIA and Microsoft and AMD. So I guess, like most of those developers being System Verilog people, the choice is kind of obvious. But yeah, I would be curious to see how we could, enable more cores in the future. But certainly that's not a goal at this point because, we want to have a stable set of features. It's a security project, so our focus is making sure that things work. But there's no reason really that you couldn't, use a different core. And I'm sure that there might be, research or other efforts that might try this out, right? And so, what's the question there? I see. So the question is whether anyone's looking at doing System Verilog AMS, which is kind of more open source friendly, let's say. We're not looking at it right now, but we're certainly happy to talk about it and see if we should be looking at it. I mean, I've heard about it, but I think that the problem in this space is, of course, everyone has a bit of a different idea how to do things, and including even the language you're writing in and the testing methodology and so on. So even getting to agreement how we should do things in Calyptra is not easy. But yeah, I mean, if you have concepts on how things could be done better and in a more open source friendly way, then we're happy to talk to you. Okay, so just a clarification that Verilog AMS is a standard that we could do open source, and so yeah, I don't know enough to kind of answer your question fully, but certainly happy to talk to you offline. Yeah. Okay.
What's the main difference with OpenTitan and Calyptra?
What's the main difference with OpenTitan and Calyptra? That's a question we get a lot, and thank you for it, of course. So of course, we're friendly towards OpenTitan, and we're actually using a lot of the great stuff that OpenTitan has built. The project was born from the need to actually do an integrated root of trust, and that wasn't originally a goal of OpenTitan at all. So OpenTitan, of course, recently I think they've been saying, oh, we can also do an integrated version, but originally it was built as a standalone root of trust chip. Originally to kind of replace the Titan, the root of trust implementation at Google. So I think that's a major difference. Now, of course, like ultimately, I think both projects could theoretically cover both use cases, because there's nothing stopping you from just taking Calyptra and making it into a chip. But it's just a different focus, and also it's just governance as well. Like Calyptra wanted to be, independent and set up as a Chips Alliance work group rather than a standalone project or part of OpenTitan. But ultimately, of course, a lot of people kind of ask this question, and the answer is obviously there's vast amount of collaboration that we're hoping for here, and the aim was never to be competitive in the direct sense. Just like in the open source space, in other areas, you'll always get 20 different ways to solve the same problem, which is a good thing. It's a good sign. So in case anyone's feeling bad about Calyptra being there when OpenTitan is also here, don't be. It's the projects are meant to collaborate rather than compete. Is there a repo for Calyptra that people could use? Yes, indeed, there is. There's one main repo. I'm not sure, I should have put the links here, but I can fix that later. So there's a main repo with links to other repos under Chips Alliance. I would say that, I'm not an expert again, but we're doing a kind of subset of the capabilities of OpenTitan in a sense. There's two kind of variants in which the chip can operate more independently and less independently of the main SoC. They have a pretty kind of weird name, right, which I never remember. Just give me a second. Calyptra. Yeah, there's boot media integrated and dependent variants. But in terms of like the actual security model implemented by those two projects, I am not the expert for sure. You can talk to Prabhu, you can talk to Matt. I suppose they'll probably be able to give you more detailed information how these two projects compare.
Thank you.
Right. I think that hopefully nobody has more questions, because we probably should go on to the next talk.
Actually, you have a few minutes to spare, but you did very well. So thank you so much for an excellent talk. That was really good. I appreciate it. So our next speaker will be Core Nielsen. He is going to be chatting with us about Calyptra, validating firmware against multiple hardware models, continuous integration. Core is an embedded engineer working for Google. He's written firmware for Google's in-house Titan root of trust chip and has dabbled in Rust firmware development since 2015. Is now leveraging Rust to develop secure, maintainable firmware for Calyptra. So Core, are you able to share your screen and present?
Can you guys hear me?
Yes, and we see you as well. Thank you.
Let me try to present here. Let's see if that works. All right.
Thank you. Thank you for joining us today, by the way.
Yeah, sorry. I would have liked to be there in person, but unfortunately I ended up with COVID at the last minute, so I'm going to stay home. Okay, whoops. Hopefully the presentation is working. Is that right?
Yes.
Okay. All right. So thanks for the introduction. I added a GitHub link at the last minute to the Calyptra firmware repository, which is where all this stuff lives, including our actual RTL for the FPGA test bench, even though it's not technically software. The software team wants to own it. You can follow links there to the main repos too. So what I want to talk a little bit about is testing the Calyptra firmware, and this is going to be a bit lower level talk than the last one. So maybe just first a little bit about just software testing in general. We have unit tests, and these are, great. Everybody uses them. They're fast to write. They fast to execute. It's really easy to do coverage guided fuzzing. So what this means is where you can execute the test case in an environment where the input to the test is generated based on how the fuzzer sees the code run. So it can create input for the test to try to find interesting branches and other problems and just explore the possible state space of the code. And unit tests are a great way to do this. But unit tests also are not really great when you want to say, hey, is this firmware safe to put into the put into the ROM? Because for one thing, they test source code. not the final compiled machine code. So if there's compiler bugs or other issues like that, the unit tests aren't going to really help you find those, because usually they're being compiled for a different architecture or using obviously different optimization passes and whatnot. They're unlikely to notice runtime issues like stack overflows or watchdog timeouts. It's very difficult to write unit tests that interact with the hardware. You can, but oftentimes you end up kind of doing a lackluster implementation of the hardware as part of your test case that doesn't behave the same as the actual hardware. And from my experience, this tends to be very error prone. And then oftentimes, to enable some of these unit tests, you have to create abstractions, and depending on the language you're using, those abstractions may not be zero cost. Rust can help a bit here, but it's still, this is an issue that plagues many C code bases I've seen. And 100% coverage isn't realistic, because there's lots of kind of glue code and stuff like that that you can't. That's part of the firmware. That's not part of the unit tests, and they're often brittle because they're testing components of the firmware rather than the firmware as a whole. So as those internal bits change, you oftentimes have to update the test cases. So, and so for validation, we kind of prefer to use integration tests, and we can run these against the final machine code. They can be executed against an RTL environment, so where the firmware is running, inside the final RTL that it's going to be bundled with. And we can discover any bad assumptions that the firmware makes about how the hardware behaves. We can sometimes even discover hardware bugs. And 100% coverage is possible, right? Like, it's theoretically possible to write your integration test to cover every single branch that the machine code does. And you can take your assertions, which in unit tests are typically part of the actual running binary. So if your binary goes crazy and has some kind of crazy memory issue or whatnot, if it goes into the weeds, you might accidentally make the test pass by accident. Whereas with the integration test, because you've kind of got your test has two parts: the firmware running inside the test environment, and then it has the test runner itself, which can do assertions based on what it observes the firmware do. And even if the firmware goes completely crazy, if it's not returning the expected results, the test will still fail. But integration tests also have a lot of problems. They're usually pretty difficult to write, and so much so that it's actually pretty rare, and from my experience, for them to be kind of like cover every single exhaustive case that the code can handle. And you oftentimes have to run these tests in different environments, and it's you write one test that runs in some like UVM environment, and another one that can run against, say, an FPGA or some full system simulator you're using. And it's trying to use everybody's frameworks as they're meant to be used tends to be, I'm writing the same test 3 times depending on which environment's running in, and that's not really very fun or a good use of time. And it's also pretty difficult to do coverage guided fuzzing, because typically the way the open source fuzzing frameworks work is they insert symbols into the final instruction stream that basically keep track of where execution is going, which is great when you're running on a big fancy host CPU, but your embedded firmware CPU probably doesn't have enough RAM to hold those extra instructions, and doesn't have a place to put the actual results, which oftentimes are multiple megabytes of data. So you can do this with help from the outside, where if you want to change your RTL or your CPU to keep track of where execution is going and write that somewhere, you can do this stuff later, but it's actually pretty hard to do. But some of the stuff we can fix. I mean, we can make integration tests easy to write. We can make them so that they are exhaustive, and we can make it so that we can write a single test once that executes in multiple different environments, which is kind of the what we're trying to do with Calyptra. So just before we go, let's talk a little bit about just general, very high level block diagram. It's very simplified, just to point out the parts that I care about for this talk. So just don't use this for anything that matters. But in general, the way that we think about the hardware from the test point of view is we've got the SoC management CPU. So this is the thing that's talking to Calyptra. And there's this APB bus that Calyptra exposes. So if I go over to its Calyptra top RTL, which is like the main Verilog module, it has these APB signals, which are wired up usually to some fabric in the SoC that some management controller will talk to. So that APB bus here is generally what we want our test case to manipulate. So we want to be able to basically generate any possible memory transaction on that bus from the test case. And using that bus, we can do stuff like fill in the fuses. We can we can write commands to the mailbox, which is the main way to communicate with the firmware. And we can do a bunch of stuff like set various configuration signals and whatnot. And then the Veer CPU inside Calyptra, which is running the firmware that we actually want to test. So this has access to a bunch of peripherals, cryptographic peripherals, has access to the ROM, has access to SRAM. All that stuff is kept secret from the outside world by the hardware. And we want to test the firmware that's running inside that environment. So I'll just go again through the RTL here. I mentioned the APB bus signals. We've also got some reset signals that tests might want to manipulate. We have the obfuscation key, which is a silicon secret that Calyptra uses to obfuscate the fuse secrets. And then it has a few status bits that we test want to look at, and also a place for TRNG data to enter the device from the outside. And then as well as the various security state related stuff, which is for whether debugging is allowed, that sort of thing. And the behavior of the firmware changes depending on some of these signals. So the test cases need to have a way to manipulate them. So just again, going back to the APB bus, we have this, all of our registers are using, what's it called, System RDL, I think, which generates a bunch of great register documentation. And also we generate all of our code to access these registers based on that too. So the test cases can easily access any of these registers, the APB registers that are exposed to the SoC whenever it wants to, and can do so in a pretty nice way, which I'll show later. Oops. So just kind of scroll around. We got the ability to lock the mailbox, check the mailbox length, execute it, set all the fuses, which are done only at startup, ideally being done by a hardware state machine and not the SoC CPU, but anyways, we'll talk a little bit about the various different power models that we're using. So the first one is the one that's basically not using the real RTL, because at the time we started working on the firmware, the RTL didn't really exist at all. So we built basically just a Rust library that consists of a RISC-V emulator, basically trying to emulate the Veer core. Or interpret like an interpreter for the Veer core, and then a bunch of the various peripherals as they were documented by the hardware folks that we didn't quite get right, but over time, as we tested, in this environment and other environments, we were able to converge the full system simulator to behave the same as the RTL, at least in the scenarios we care about. And the tests compile to self-contained executables that can run on Linux and Mac OS, and they can probably run other places too, but I don't think anybody's tried. And these tests are running really fast. Like we can run our entire test suite. This was, I don't know, 50+ tests that are booting Calyptra, many times, and we can run that test suite in just a few minutes. But it's not super high fidelity. Obviously, the timing is not accurate. The real hardware is, takes a lot longer to do crypto operations and whatnot. But these are great as kind of did we actually break anything really significant? And so we run these test cases for every commit. So before you can even merge your PR into the repository, these tests have to pass under this full system simulator. Yeah, we can run our production firmware in this environment, so we don't have to compile anything special for it. Ideally, we can take the final binary that goes to tape out and run it here. We can do some fancy stuff like get it to tell us some coverage data where it went, which is just a little bit of code in the emulator to do that. And we can log the CPU bus activity, which is pretty great for debugging certain things. And we can even simulate some impossible scenarios like bad hardware, or one scenario that I'm really interested in is glitch resistance. So this is where you have an attacker who's manipulating the clock or the reset signals, or maybe even the power supply to the CPU or to the whole SoC, and trying to trick the CPU into like skipping some instructions and to maybe get past code verification or something like that. So we can add hooks to the interpreter to basically simulate skipping branches or corrupting register contents and stuff like that. So you can imagine, and I haven't done this yet, but I'd love to be able to run millions of iterations where it's randomly trying to screw around with the CPU registers or the CPU execution, and then see if, hey, does Calyptra ever let non-validated machine code get into the instruction memory or whatever, right? So that's kind of our our main test environment, but not super accurate. And then 3 or 4 months ago, we started working on a second model, which is a Verilator model. So this model is built against the real RTL, and it's high fidelity, cycle accurate. So it's actually compiles pretty fast. You can make a change to the RTL and then see the change live running the real firmware, usually within a few minutes. In this case, the APB bus reads and writes. These are basically the test case itself, or the infrastructure behind all this is manipulating the actual signals being passed to Clipper top. Because of that, it's very cycle accurate. Your test case can, be really fast. Like, well, what happens if this signal happens at exactly this time? What does the firmware do? That kind of stuff, which is kind of really nice, trying to dig for little weird timing edge cases and whatnot. But the downside is that execution is very, very slow. Just to do a single boot of the Verilator test takes, hours, like an hour and a half, I think, just to get Clipper to boot all the way to runtime firmware right now. So, it's not really feasible to run, 100+ tests on every commit if it's going to take, 7 days of a relatively powerful machine to run those tests. So we don't actually run all our tests, but we do run nightly some what we consider important tests that kind of test the success cases and stuff like that. It's also a great environment for debugging. So, I can just by changing the flags to how I run the test, I can have it write out a BCD file that contains all of the Clipper signals, which is great for trying to give to the hardware engineers when trying to track down a bug. Or you can have the test or the environment basically just parse all of the bus activity and log it to a text file, which makes it easy to grep and whatnot. This is basically the best place to debug issues with the hardware or the firmware when you're not sure what's wrong. Unfortunately, Verilator is not perfect. It doesn't handle every single thing that Clipper's RTL can do. So one case I know that's a problem is that we can't actually put the CPU to sleep and expect everything to work properly right now, which I understand. I haven't really looked into this much myself, but I understand it has something to do with Clipper not supporting some kind of clock gating, or sorry, Verilator not supporting some sort of clock gating or something. And then this new model, which just started working this week, is a real-time FPGA model. So here we're trying to target the ZCU 104 dev board, which is roughly $2,000. And this thing barely fits Clipper. We actually had to trim down some of the number of key vault registers and stuff like that to make it fit. But it was the kind of most reasonable choice given the cost and size constraints that we needed. And so this has the Zynq FPGAs have this application processor, which can basically run Linux and run Rust binaries. So we can just compile our test cases to run this A53 processor, and then those test binaries can just talk to the APB bus using MMIO directly. So it's super fast and super great. This environment here is probably, hopefully we can start running test cases on pre-submits with this. So we'll need a little farm of FPGAs in somebody's basement somewhere to execute these tests. But yeah, I'm hopeful that this will become part of our standard CI to execute everything in this environment. One of the downsides to it right now is that we are using the clock signal that's being generated by the oscillator on the board. So the test case itself doesn't have any control over single stepping or trying to control the test. So there's some test cases that involve timing that we can't really run in this environment. But you can imagine that with some tweaks to the test harness, we should be able to give the test control over the clock and do those sort of timing things in this environment as well. And the main downside to the FPGA is just that if you want to change the RTL, it takes hours to recompile the bitstream, and it's not a great prototyping environment for RTL, that's for sure. But as an environment that tests the firmware, it's fantastic. If you want to do now, maybe is just go through a couple of demos of just the test running in different environments if we have time. I'm not quite sure what time I started it. I'm sorry. I think I'm maybe 20 minutes in.
Yeah, that's correct.
Okay. So let's see here. So I'm going to share a different tab here. So this one can, here's kind of a basic test case that's doing a basic scenario here. So here we're just creating the hardware model itself, and so this, depending on basically the environment variables or the configuration flags to the test, it will instantiate the various models. So you can write the test once, and then depending on how you want to run it, it'll run in the different environments. And the idea is that almost all of our tests should be able to run in any environment you want to. The only real factor being how do you want to wait for it in the case of the bare layer tests. So here I'm basically saying, hey, I want to create a new model. I'm giving it some initialization. I want to use this ROM, please. So I'm just building our regular ROM. But I could pass in a ROM that is testing some specific hardware feature or something like that. If it doesn't necessarily be the actual production firmware, but in this case it is. I'm telling it, well, I want the security state to be our production security state. So this is where JTAG's disabled, and this gives us access to all the secrets. If JTAG's enabled, you can't use any of the secrets. And then it's telling the model, saying, hey, I want to run this kind of special flow, which is where it's setting a special register, saying I want to run this flow that's normally done in manufacturing, and generates the certificate signing request for Calyptra, which is done early in manufacturing. And then we can receive the actual request from the mailbox and then parse it in SSL. So, again, because this test case is not running as part of the firmware, but it's running outside the firmware, it can use libraries like OpenSSL and other things to just parse out, the X509 and do what it wants to do. And again, even though these are integration tests, they are written like as if they're unit tests. So you can just, run the test in the IDE, and there it goes. It ran the test, ran really fast, right? And it's pretty much as fast as a unit test, even though it actually booted Calyptra inside the emulator. And you can see our debug version of the firmware here printing out everything it's doing. And then here's the actual CSR that came out, and it was asserted that it matched the golden data. And so it's pretty great as a development environment, because you can just write these unit tests as if they're unit tests. So that's the test running in that environment. I'll show another example here. So this is again running the same test, but I've added this features equals varilator, which will run it in the varilator environment. As you can see, it's running really slow. Already it started at, it was 4,000 cycles in. It wrote set the value of the boot FSM, but it hasn't even printed the first line yet. So I think it takes around a minute to print the first line, but as you can see, this isn't very fun. I'm just going to Control-C it before it actually prints anything. But one of the things I did mention here is, hey, I want to write a trace to this file here. So if I Control-C this, and I'm going to take a look at this trace file I told it to write. And this contains all the activity that it saw. So here we can see the SOC from the test case, basically writing to various probably fuse registers and various things and preparing. And then you can see the microcontroller, which is what we call the Veer core inside Calyptra. It starts doing a bus activity. And here you can see it's clearing the main memory. It's clearing, our main SRAM, which is what it's been doing, and probably what it's doing when I stopped it, right? So, you can get one of these trace files for the whole boot and try to track down what's going wrong. Or if you want more detail on that, you can have it write all I have to do is just change this to BCD, and then that gives me a nice BCD file that gives all the signals in Calyptra, which you don't really want to use with the full firmware, but if you have an isolated test case, you can usually get something to send to the hardware engineers to debug their RTL. Or you can look at it yourself. And then I'll take a look at the same test case, this time running in the FPGA environment. And I kind of forgot to test this today, so hopefully this works. Let's see. Yeah, there it goes. All right, so it's a little bit slower than the software emulator. And I think that's just because we haven't really got the clock set, to the ideal speed yet. But you can see it booted the whole thing. This is still very early. The clock cycle counter is not quite accurate yet. I think that's just like real time or something. But the test ran, it passed, and if I add the verify here, it should show me the certificates. Oops, that's not. Sorry, no. Should show me all of the certificates that were generated by the firmware. But yeah, that's basically kind of a quick demo of this. And I don't have a whole lot more to talk about other than we also provide C bindings to these hardware models. which is great for vendors who oftentimes want to test their integration logic against like an accurate model of Calyptra, and so they can use the emulated model if they want something that runs fast, or the Verilator or FPGA models if they want something more accurate. And yeah, I think that's pretty much it. Any questions? Excuse me.
I actually have two, if I may. So if we can go back to Verilator, the slide there, you mentioned a bunch of things. So first of all, you said that execution is very, very slow. I mean, it's partly expected, but on the other hand, I'm interested in you've been investigating the changes we've been doing, both in terms of execution runtime, but also you mentioned compilation was kind of long, because we have been optimizing this for
compilation is surprisingly good. Like I said, I can compile almost all of Calyptra on my workstation in like maybe 2 or 3 minutes. I'm actually really impressed, and most of that time is not Verilator itself; it's actually the C compiler compiling the C code.
Okay, I see. Yeah, because it takes several minutes. For me, it was long, but
yeah, of course. Yeah. I compared to the FPGA stuff or vendor to other proprietaries I've used, I'm actually very impressed with the performance of Verilator. It seems to be faster on the same hardware, and the only real issue is that it's maybe not quite as accurate. And I'm hopeful that will change someday.
So, but it would be interesting to have a conversation about, why is the execution so slow, and if that could be improved, because like we are looking at these things in other contexts, and even if it's not anything we can do anything about, it's still useful to understand where the bottlenecks are. And
yeah, well, if someone wants to do some tuning on Calyptra as an example, I would be totally in favor of that. Please contact me if you want some help.
Yeah, we'll definitely be in touch. And the other thing is that you mentioned Verilator does not support everything in the RTL, and certainly that's another thing that that one is for sure something that should be fixed.
Yeah, and I have to talk to our RTL folks to find out more details on what those problems are. But in the case right now, basically everything except for low power stuff works great. I haven't found a scenario that doesn't in Calyptra that doesn't work outside those Veer low power things.
And the other thing was about the FPGA emulation. I mean, it's all great stuff, by the way. I really like the testing methodology, but have you thought about co-simulation between, so for context, we have a simulator called Renode that can do like co-simulation with Verilator. So you'd run peripherals in Verilator and you'd run the core in a fast instruction set simulator, which potentially you could get pretty good performance and pretty good fidelity at the same time.
This is something that's definitely possible, and I would love to do it. It's just a matter of basically exposing the internal HB bus to all the peripherals to a test harness. So it's really just writing a bunch of RTL boilerplate to kind of link that stuff back, and writing the actual hardware model should be pretty easy to take our RISC-V interpreter and hook it up to the HB bus of a Verilator instance. So yeah, I'm very much in favor of this. That said, I'm not, and I really want to do this before, but now that we have the FPGA working, I'm not quite as excited because the FPGA, is almost as fast and handles most of the stuff we care about. If I had infinite time, I would absolutely do that, and I think it's a great solution.
Thank you. All right, I'll pass it on to other people.
Hello. I actually also have two questions. First one is much faster, though. Out of curiosity, for the FPGA, the bitstream creation, and also the simulation running, are you using like a third-party tool chain, like FireSim or something?
No, this is just using Vivado and a TCL script. So we just have a TCL script that just generates all this, basically interacts with the Vivado garbage or proprietary stuff, and then generates the bitstream at the end. And then, as far as our CI cares, it's really just a black box that takes in RTL and returns the bitstream.
Cool, thanks. Second question, it kind of comes from a lack of understanding, my own lack of understanding of how non-cycle accurate simulations run. Could you go to the hardware model number 1 slide? So it mentions low fidelity, and so it's not clock cycle accurate. So do you ever encounter a situation where the emulator actually gives a result that is actually not accurate to how the real system would run if it was running cycle accurate?
Well, a great example where this would happen would be, say, something like we're testing a watchdog. Like, are we setting a watchdog timer correctly, right? So the watchdog timer is going to be set in cycles, right? And so the number of cycles it takes to get to a particular point in the time, on the real hardware, it's going to be different than what it is in the simulator. I mean, it's not impossible. We could, obviously, people that are writing, Nintendo emulators, they get the stuff right. But it's a lot of effort, and it isn't that important for us. We can have certain tests that are testing some of these more timing related scenarios, which there's not many. Like for the most part, Calyptra doesn't care about time at all. But it's we're happy that we can test those things in one of the more accurate environments. And we don't necessarily have to, when it comes to something like a watchdog, you really care if, oh, my watchdog fired 10% early, yeah, not really, as long as you before you release the final build, that you're running it in a more accurate environment, or running the test in a more accurate environment. So again, most of this, what tends to happen is working in the Verilator model, I'll notice, hey, this test case doesn't pass in Verilator, and find out why that is. And it turns out, oh, actually, there's a bug in the peripheral in our simulator, or the peripheral doesn't actually behave the same way as the real hardware. And sometimes that's because there's a bug in the hardware, but more often it's because we misunderstood the documentation and implemented it incorrectly in the emulator. So over time, because we're running the same tests in all these environments, right? Whenever something goes wrong in one environment, not the others, and we're like, okay, there's something wrong in one of the environments, and that's when we try to figure out why that was.
Okay, thank you.
And I would say, yeah, 80% of the time it's because us software engineers misinterpreted the spec.
Thank you so much, Core, for your great talk, and I do hope you feel better.
Yeah, thank you.
All right, so our next talk is Jocko Hoffman, who was from Western Digital. Talk is entitled OmniExtend, Coherent Scale Out, excuse me, over Commodity Fabrics. He is a member of the research organization at Western Digital. His research interests include application-specific accelerators, coherence, and open source hardware design tools. He holds a PhD in computer science from TU Darmstadt. Thank you.
Now we got the slides up. How does it work? Oh, I have to join it, or can I just? Well, then I have to do that. No, wait, I do it somewhere. I was not aware of to join. Do you have Chrome? Yeah, I do. It's okay. Sorry about that.
That's okay.
It's here somewhere.
I can resend it to you if you need me to.
It's just a meet. This one? Yes. You just join. Should give you a companion note. Present or ask to join? Okay. Or it presents very. Okay, sure. Yep. Well, sorry about that.
No, it's okay.
To get it to actually allow to move that. Okay.
You're in. Good.
So let's see if I can share this. Where can I start? Someone there.
Okay.
Wonderful.
Good. Thank you.
Sorry about that. I didn't know I have to enter the meeting itself. So let's get started once everyone's settled again. Thank you for the introduction, Rob. My name is Jörg Hofmann, and today I'm going to talk a bit about what we did in the OmniExtend space over the last year or so, and the recent open source releases we had, which you can find on GitHub. Just to give you a quick overview what I present today, I will also go into detail what OmniExtend actually is, but just give you a high-level overview. We have released a memory endpoint for OmniExtend, which you can use to expose any kinds of memories, AXI attached memories, like HBM or DDR over Ethernet, and that's the important thing, it's coherently. So To use that, we also release an Open Python to OmniExtend bridge. So you can take your existing CVA6 design and take the coherence bus they are using, the Open Python, and translate that transparently to OmniExtend. The whole thing, both of them are released under Apache 2.0, completely available on GitHub, and also has been used in on FPGAs so far, and also in simulation, which I will talk about later. So what's OmniExtend for those of you who don't know it? It's an approach to get a single coherence domain over multiple Ethernet attached hosts. So you can just use your off-the-shelf hardware. You don't need any, for instance, InfiniBand links or anything. It's just using Ethernet to be as widely usable as possible. And the whole thing is based on open standards. So for one, we're using TiLink as like the base bus on which can be found on older Sci5 RISC-V chips, for instance. And then OmniExtend is a layer around that, which deals with the whole nastiness of Ethernet being not in order, being like dropping packets if you're unlucky and stuff like that. So that's the Omnex part around this. And the goal of the whole thing is to give you fast load store access to huge amounts of memory over Ethernet. So how could the system look like? The red parts is what I brought to you today, but the gray parts are other things others are working on or others presented. So as I said, you have the CVA6, which is connected to Ethernet, and then it can access some memory from let me get a pointer, from over here, which is, for instance, some DDR4. And then you can have user space software, which also accesses the same data, for instance, loading some firmware image into the memory, or even another CVA6 working together, booting a Linux on multiple cores. You could do stuff like that. Other approaches are like a storage NIC, where you just have your normal network interface, which speaks OmniExtend and which could do stuff like RDMA-like operations, but you could also with CXL.mem really do some kind of coherent access to the Ethernet attached memory. The whole thing is available, as I said, on GitHub. So if you want, you can just use these QR codes. And the memory endpoint itself is designed to run on FPGAs. The open source release targets 10 gig Ethernet just because of availability. And it's really easy. You can just buy a $100 switch on Amazon if you want to, and get this running with relatively cheap FPGAs. So it's very easy to use even for, let's say, resource constraints organizations. It uses AXI for memory interfaces, which targets a bunch of memory controllers which are available. So if you're running a Xilinx FPGA, you usually have like HBM or DDR4 or all other kinds of memories. The endpoint supports the whole stack of TiLink operations. So apart from the coherent accesses, you can also run, let's say, atomics if you need that for your application, or non-coherent accesses, which are interesting for like bulk transfers. And the whole thing also acts as the lowest points of clearance. If you want to spin your own OmniExtend hardware, I extracted the OmniExtend logic out of the whole thing, so you can also use the same codes for your own applications. The other part, the CVA6, is 100 gig compatible, and gives the CVA6 the transparent access to the endpoint memory or any other OmniExtend compatible memory. And in addition, I also have a software library which gives you the requester interface, so you can talk from the software to the endpoint, so you can play around with the whole software stack, and you can also easily debug the whole stack to see where it locks up and so on. So how does OmniExtend look like, or what does it give you? As I said, you have different types of operations. That's the whole TiLink stack of operations. So you have atomics, you have non-coherent and coherent accesses. It supports burst transfers, so you're not constrained to tiny loads and stores. We can do, let's say, cache line sizes of 512 byte, or you can do smaller, bigger, up to the maximum is really set by the Ethernet. So when you have jumbo frame, you can do about an 8K read or write. OmniXTend gives you the flow control mechanisms. As I said earlier, Ethernet is not really suited well for these kinds of high reliable protocols, because what happens on a CPU, if a message gets lost, it will just log up usually. There's no recovery because it's assumed that's not really happening. For Ethernet, we have to assume that, so OmniXTend gives you a way to deal with the out-of-order transfers, drop packet detection, and how to handle that. The memory endpoint is compatible to 103 and what I call 1.1, which adds some convenience features onto OmniXTends, like dropping and creating connections, so the system is less static. It's completely implemented in RTL, in this case PluSpec, which is sadly a bit not well known, but completely available now under BSD3. On GitHub, and it's a highly productive RTL. So it's not doing high-level synthesis or anything, but it's a very, very productive way of describing hardware down to the lowest registers or whatever. The endpoint is device independent, so I've tested it on a variety of Xilinx/AMD FPGAs, but you can also run it on let's say Intel FPGAs, or you can run it on SkyWater 130 or something similar when you bring your own SRAMs, basically. As I said before, we have 10 gig power there and attaches to AXI. So how does it look like in a very high-level view? You get a 10 gig Ethernet stream as AXI4 stream in there. Then we have an OmniXTend handler, which deals with all the nasty Ethernet stuff and gives a channel separated and in order view of the messages to a tiling handler. Then that's buffered into input FIFOs to deal with flow control, and then split onto the different channel handlers, which deal with stuff like coherence or non-coherent requests, atomics, and so on. Then again, for flow control output, credit handling, it's distributed again to different output FIFOs, which are then packaged in a sender. And for one, kept in the resend logic for later use if you actually drop a package, or if not, like it goes also over Ethernet and you hopefully receive it on the other end. If you want to use your own hardware, you can basically get everything that's not Cray in what we have released. And the Cray part, you have to bring your own. Bring yourself, but it's relatively easy to add your own tiling compatible design to this architecture. The prerequisites to just get going are relatively low, and everything's open source. So you need the PluSpec compiler, which you can get. There are releases for like Mac and a variety of Linux distributions readily available. BSV Tools is just a little packet which provides some make files to make the building easier. And you need Rust, which luckily is also open source. And Rust is used for the interface, the simulation. If you want to go to synthesis, of course, you have to use your favorite Verilog flow, which calls PluSpec in the end produces Verilog, and then the Verilog can be ingested by whatever downstream tools you use. If you want to just use Xilinx design, you can use Tabasco, which packages the whole thing and gives you a bitstream and makes it available over PCI Express, and sets all the Ethernet stuff up. The GitHub also contains precompiled IPXec Verilog releases, so you can just plug and play if you want to. In addition to the hardware, I also provide the software implementation, which is entirely written in Rust and gives you not that high performance, but rather correct implementation of the requester library. So you can do read and write requests in, let's say, atomic, let's say, coherent or non-coherent forms. And it's very useful for debugging, testing, and you can do the whole full system simulation through those tools in hardware, or if you want to, you can run it on your PC or a laptop or whatever to do a whole system simulation. There's also some helpful tools included. So OmniExtend RS is just the OmniExtend library, which you can use in your downstream tools if you want to. OmniExtend TUI, which brings you a terminal user interface to really just do peek and pokes to see what's in the cache, when does it get invalidated, which is interesting to play around with. Bitload, if you want to, let's say, load a bit stream into the into the Ethernet attached memory, and config for reading status registers to see what's going on in the hardware. The simulation looks pretty close to what I showed earlier with the full system view, but instead of adding Ethernet in the middle, I'm using Linux virtual Ethernet devices. And then you can run the whole stack. We also provide a Wireshark plugin if you want to see the messages, which nicely parses those and shows them to you in a human understandable way. Let's see if this video works. Sadly, those here in the room might have a hard time seeing it because the screens are a bit small, but I will try to stop. So I'm just starting it, so nothing interesting happened yet. And that's the script I provide, which starts on the top left, the simulation, and then you get 3 of those TUI windows, which are basically 3 clients for this memory. And you can do a variety of reads. So the simulation starts, gives you a bunch of messages, and then you connect, now, for instance, on the top right to the endpoint. And the endpoint hopefully responds. So you get a little green connection active, and then it's starting to run. I connect some more, and I do a cached read. So the cached read will be shown on the bottom right of the, let's see if I can get the pointer again, on the bottom right of the window. So we now have loaded the cache line and on crunch mode because we have only read it. We haven't written anything, so we don't have exclusive access. That's what Entire branch is. And then we go on, do a cache write. Now we are in trunk mode, so we have modified it. And when we now go on and read from another, that's happening on the bottom left. And then we written again and are now in trunk mode down here. And the top right went into none mode. So you can use this whole system to play around. And the same software you can use if you move to the FPGA or ASIC to do the same experiments on hardware. So let's go on, exactly what I'm showing here. So when you go onto hardware, you can go use the same software and analyze your system behavior. Just a quick overview, how fast is it? With a lot of caveats. The hardware protocol is not well suited for software. It's also not using stuff like DBTK, which would also improve performance. But that said, the software can saturate a 10 gig link at 4 kilobyte chunks. Can do a bunch of requests, so up to 2 million requests per second with batching, and the average time per request, which is a bit tricky, it's the total requests divided by runtime, is about 484 nanoseconds, but again, as with batching, the average latency is much higher, 69 microseconds in this case, and if you tweak a bit, I got it down to 3.8 microseconds. That said, it's in software, in hardware, it's a lot faster than that. The OpenPython to OmniExtend part has been developed by Lewis Communications and provides you transparent access to this memory, for instance, the memory endpoint, and it's based on OpenPython CVA6. Transparently translates these OpenPython requests to tiling. So if you already have OpenPython in some project, you can try and add this translation layer to see how it would work over OmniExtend. There is a tightly coupled simulation right now available with the OmniExtend endpoint, but the VF socket simulation is right now not yet available, but that will be coming soon, hopefully. How does it look like? You have Xilinx FPGA with the CVA6 in this case, which has multiple levels of caches. In this case, we have a level 1 data and instruction cache, and then an NOC. And the NOC attaches to the Xilinx, the network on chip, attaches to the Xilinx 1.8 interface, encapsulates those into the OmniXtend 1.0.3 format, and then sends it out over another open source tool. That's the Lewis 100 gigabit Ethernet MAC, which is also completely open source and available on GitHub if you need a 100 gig MAC for instance for Xilinx FPGAs. And the translation is also pretty straightforward. It takes the OpenPython messages from the NOC, puts it in some files, translates it to the format that the Mac needs, and sends it out over the LMAC3 core. Yeah, as I said, the main thing that's still missing is like integrating the CVA6 into the socket-based simulation to make it even easier accessible or better accessible. Apart from that, it's ready to experiment, and I'm glad we also have some users with interesting questions and fruitful conversations, and I hope more will come and play around with this. Apart from that, thank you for your attention, and yeah, I hope for some interest. Thanks. Any questions?
Questions in the room? Questions online?
Okay. Oh.
Any special support for things like IPv6 and what you're doing?
There is no IP involved at all. So our protocol sets up much on a lower layer. So we don't use any IP, we don't use any TCP. It's not its own protocol.
Any other questions from the audience or online?
Okay, thank you again. And
Thank
have a
you.
great day.
Appreciate it. All right, so our next speaker is Jack Koenig, who is going to be chatting about Chisel 3 and beyond. Jack is a senior staff engineer at Sci5, where he works on digital design methodology. He is active in the open source community as a maintainer of Chisel hardware description language, and he holds an MS in electrical engineering and computer science from our friends across the bay here at Berkeley. So, thanks, Jack. All right.
Okay, just sharing my screen. Hopefully you can hear me okay. Okay, so hi everyone. Thank you for the introduction, Rob. So I have been introduced, so I'll just kind of dive in. And this is maybe my second talk in person since before the pandemic. So sorry if things are still a little rusty. It's nice to see people in person, but it is a different experience than just the little boxes on the screen. But I'm glad that all of you are here as well. So good to see everyone. So what I'm going to talk about today is Chisel, which probably most people are at least somewhat familiar with who are attending this meeting, but there always are new people. So I'll give a little bit of background. I have like 4 slides kind of explaining what Chisel is, and then the most of this is for Chisel users. So sorry if you don't know anything about it, and that's not enough of an introduction, but it's mainly going to be about features and what's been going on. So first of all, what is Chisel? It's an acronym, or better, a backronym for Constructing Hardware in a Scala Embedded Language. It is a domain-specific language where the domain is digital design. This is just like Verilog is a domain-specific language where the domain is digital design, just distinguishing it from general-purpose languages like Python, C++, or Scala. It is neither high-level synthesis nor behavioral synthesis, so it is not C to gates, it is not Scala to gates, it is a program. You write a Scala program, and the execution of that program constructs a hardware graph. That hardware graph is turned into Verilog, which you can then use with your standard tool flows. Why it's embedded in Scala is because Scala as a general purpose programming language has a lot of things that we in the programming languages communities like parameterized types, object-oriented programming, functional programming, and static typing. These are things that are popular. You know, the previous talk talked about Rust a lot. Rust is another one of these great languages with these great features. And there's a reason why they are growing in popularity. And it is intended for writing reusable hardware generators, aka libraries. The goal of being productive in writing software is you can leverage other people's software. The goal of all of this open source work is you can leverage other people's work. And in order to do that, it has to be reusable. And our experience has been that, you know, Verilog especially, but VHDL as well, it can be hard to write things like you can reuse at some level, right? This is why we have bus protocols, but that is a very specific and well-defined level. There are a lot of other places where you'd like to get reuse, and it's harder to do. And we hope that different language constructs can make it easier. So I mentioned that Chisel is not high-level synthesis, and so it's important to point out that it is, you can write something kind of like Verilog. I'll note that this is very much like synchronous, you know, digital design. We're not talking about anything analog. We're not talking about, you know, all the kind of the weirder, more electrical engineering-y aspects here. It's mainly just the functional description of what you do. But at that level, which you often write in Verilog, you can write things in Chisel that look very similar. So, you know, let's not worry too much about the syntax here, but this is just a basic module that has ports. We've got an input, we've got an output. It's parameterized by a bit width. We've got a couple registers, and we're just summing a value over 3 cycles where we have, you know, 2 registers with the previous 2 cycles version of it, right? And so this is a 3-point moving sum, but what would happen if you wanted more than 3 points? What if you wanted different weighting for the values from previous cycles? What we really want is a generic FIR filter. And so in Chisel, and I will not dive into this code, so just trust me, and you can go run this example. This is an example that is parameterized. My mouse may or may not be visible. I'll just not do that. But it is parameterized just like the previous one on bit width, but it's also parameterized based on the coefficients that you want to use in your filter. So that is, it is a sequence of uints, which allows it to be, you know, the number that you have is parameterizable as well as their values. And so this lets us completely make it generic in however many cycles we're filtering over and how we're weighting the different pieces, the different delayed values. And so this allows us to parameterize by those with no loss in the quality of the RTL that's going to come out. You can do the exact same moving sum filter before with this more generic version. But what's nice about the generic version is you can also have you could express a 1-cycle delay filter. That's just a register, but you can do that. You can do a triangle filter with different impulse responses. And so the point of Chisel is allowing you to write this sort of thing, where you can be as parameterized as possible with no loss in the quality of the design you're building, no QOR impact. Okay, so that was for the people who don't know what Chisel is. The rest of this is mainly for our users, so apologies to the rest of you. But there's been a lot going on. This is probably the most recent content I've ever had in a talk, which is really exciting. So first of all, this has been the longer term effort, but we have a new compiler underneath Chisel. So Chisel emits an IR called Fertile, and then Fertile has a compiler that compiles it down to Verilog. We used to have our compiler implemented in Scala, similarly to how Chisel is implemented. Now it has been re-implemented with MLIR. MLIR is a kind of a generalization of LLVM. It's part of LLVM, and it's for writing custom compilers. Importantly, it's much faster and uses a lot less memory. That's like a great thing. But the real goal of it, with those benefits aside, because those are very nice, it's really more about more rapid feature development. So MLIR stands for multi-level intermediate representation. I think it was originally machine learning, and then a very convenient re-bacronyming to multi-level. And it allows for coexistence of multiple IRs. So what's really convenient here is you can have your Fertile IR, and next to it, you can have some specialized assertion IR. You can have those both lower into system Verilog and things like that. So it makes development of new features much, much easier. Now, part of this move to a new compiler, this is a common issue when you have large infrastructural change, is a lot of older features kind of, in order to make development easier, we had to drop some of our older features. So the old Chisel 2 compatibility layer is now gone. Fixed point and interval types are gone. I'll talk about fixed point in a second. And the old Scala Fertile compiler APIs, which were nice and I use them a lot, are no longer there either. But the benefit of this is that the smaller public API surface is making development a lot easier, and you're going to see we're finally starting to reap the benefits of some of that pain. I'll note that there's ongoing work on FixPoint to make it a library. So I recently saw the library work here. I think there's some improvements we should make, but it's not fully gone. It's just gone as like a primitive. So it's just some other minor organizational changes. We've renamed Chisel from Chisel 3 to Chisel. I feel like every project goes through this. You have like version 1, 2, 3, and then you just go back to no numbers. And our artifact is now officially under CHIPS Alliance, whereas it used to still be under the old Berkeley organization. We've changed our versioning scheme from kind of a Haskell style PVP where the major version was 3.6, like the 6 part was part of the major version, which is now that everyone has moved to December, confuses people. So we have moved over to now it is Chisel 5 and then Chisel 6. Don't worry about it, it's kind of reserved for possible future use. And Chisel 5 has been released and Chisel 6 is on the verge of being released. We also monorepoized it, which has made my life a lot easier for doing releases. When you have to coordinate across lots of repositories, it slows things down quite a bit. With the caveat that Circuit, of course, as an LLVM project, is in a different repo. So we kind of pull that in as a dependency, but the rest of Chisel is all in a single repo. Okay, so now what's new as of 6.0.0 M2, that M is milestone 2. This is just a way of like marking things before we're willing to call it 6.0, but I will say that we're very close to the actual 6.0 release. And most of this is from like the last 3 to 6 months. So we have much better source locators. So this example doesn't really matter too much, but what I'm trying to show is that this trait bar is in a file called file.scala in a certain directory. And class example is also in a file called file.bar, but in a different directory. It's very common that you end up with the same name. Like people really like the name utils. That's a common one. And there's other names that just come up all the time. And when you have a large code base with hundreds or thousands of files, you end up with source locators. And you look at this and you're like, okay, file.scala and file.scala, which one did it come from? I actually came up with like nice little grep tricks where you could like check if that thing existed and it would tell you that's the right one. But in reality, it's better to just have a source locator that gives you a more descriptive path. And so the new source locators do that. You'll also notice we have source locators on ports, which we didn't have in the past. That was true as of Chisel 3.6, which was released in April, I think. But one of the best parts about those new source locators is if it's unambiguous what something points to, now the tooling can use that for error messages. And so in this example, this is an out of bounds index. Bar is an 8-bit value, and I'm asking for bit 8, but we're computer scientists. We start counting at 0. Oops, I messed up, off by 1 as usual. You used to just get an error saying, you're wrong, and it's in this file. Good luck. Now, the kind of error messages that people expect in programming languages, you will get the source locator as well, but it will also pull the line and give you a caret. And I cannot tell you, like, this is such a small thing, and it wasn't even that hard to implement, but it's amazing how much nicer things feel when you get this kind of error reporting. And also in the, that was an error message from Chisel itself, but we have a compiler underneath it, and that compiler has its own error messages sometimes because there's certain things we can't check. And so this is an example where this wire is not fully connected under all circumstances. And so you get an error saying it's not, and then you get this other representation that doesn't look like the Chisel you wrote because that's what's the compiler seeing. And so now with Virtool and these better source locators, it will point you to your original Chisel to tell you where you messed up, which is very handy. Okay, I mentioned that performance is a lot better now, and that's a big one. People like performance, and it makes easy graphs. This is a synthetic benchmark because I was more interested in spending time working on features than on making really good and fair benchmarks. But in this case, I'm showing a stack of the Chisel and Fertile runtimes. And so Chisel is in red, Fertile is in blue. And so it's a combined runtime, obviously. And so for this synthetic benchmark, going from Chisel 3.5.2, which was roughly a year and a few months ago, like April of last year, to 3.6, April of this year, Chisel got twice as fast, and switching from SFC to the new Virtool circuit. Sorry, I use those interchangeably, but they're the same thing. Virtool is a part of the circuit project. That was, for this benchmark, 3.2 times faster for combined speed up of 2.5x. And memory use, similar benefits. Now, memory use is more of a max than an additive thing. So you can see that Chisel's using 18% less memory, but in this particular benchmark, Virtool uses 72 less memory. And so the overall memory use has gone down quite a bit. Now, a better benchmarking chisel is kind of hard because as it evolves, the designs I would use to benchmark it also evolve. And so I have to like backport things to do benchmarking. And that's why it's kind of annoying, but it's easier with benchmarking just Fertile because it has a spec. And so it's much easier to compare across versions. Here's some benchmarks from my friends on the Circuit project, where for a small microcontroller, kind of a larger in-order CPU, and then a large out-of-order CPU, you can see that the runtime of Circuit was from 6 to 11x faster, which is huge, right? That's much, much better. And in memory use, fairly similar on the microcontroller, 14x up to the out-of-order CPU, 4.4x. Like all this reduced memory use is incredibly helpful for our, your CI runs on your servers and all of that. All right, so performance is great, but that's not the point. The point is all the new features. So that's what I'm going to talk about. Constant types are kind of a small one, but still useful. So prior to Chisel 6, and again, Chisel 6 isn't quite out yet, but you can use the Milestone 2 release. Async reset values had to be literals, and these checks were kind of haphazard. It's somewhat complicated to implement something that will, when you base your functionality on optimizations, it leads to weird behavior and hard to understand behavior. So these constant types give us a more principled way to deal with that, such that it's very predictable, and it also supports new use cases. For example, how do you have an async reset register that is reset by a strap pin? You could, of course, just allow it, but how do you check that people are doing it right? Well, the way we do that is with these constant types. And so here's an example of the old error message in the past. It's like, this looks like it should work, but it's not known to the compiler that sum is a literal because you could assign a non-literal later. And so instead, if you use this modifier for your types called const, now the compiler knows it's a constant and it will check it. And so you get much better behavior here. And there's also possible future integration with physical design, right? Because why is it dangerous to reset something asynchronously from a port? Well, because if that value can change at certain times, you can have physical issues, right? There are like power concerns here. And so you need to constrain that port to tell the physical design tool that this is allowed. So when you have this information in your type system, you can also potentially communicate it to your backend tools. Another recent feature that is pretty big is, or this is bigger, I guess, in use cases, is what are called probes, which sometimes we'll call reference types. My brain uses both, so that's why I put both. But basically, prior to Chisel 6, there were ways to do Verilog XMRs for verification or whatever, or physical design in your Chisel, but it required like a lot of custom user extensions to the Scala Fertile compiler. And really, as a user, you don't care about that. You just want a guarantee and a mental model for how you can lower from Chisel to Verilog and how you can use it with your System Verilog UVM verification flow, for example. And so this is now at the Chisel level, we have a first-class feature to capture these use cases. This isn't that interesting of an example. It's just showing that you can declare ports that are what we call probe ports, which is something that you can read from the outside. And rather than lowering to an actual port, it will lower to a Verilog XMR. These read-write ports are XMRs that can be forced. And that's really important because for any of you who've done a lot of System Verilog verification, the semantics of force can be surprising. There are like back propagation semantics that get people, it's a really easy sharp edge to fall off on. Well, a nice thing of having a compiler is we can lower to something that doesn't have that problem, but you do have to tell us that you're going to do that. So we make you mark it as read-writable, or writable, really. Another feature that sounds kind of obvious to any compiler people, but is a good thing that we've added, are intrinsics. So I mentioned that you could extend the Scala Fertile compiler with annotations and custom transformations, but this was arguably too flexible. Like you could do almost anything, and that makes composition difficult. And it also didn't really support custom System Verilog emission, which was really problematic for a lot of the extensions that people wanted to do. Intrinsics are like reeling that back into something a lot more restricted, but because of the way MLIR works, and therefore how Circuit and Virtual work, it's really easy to do really nice custom System Verilog emission. And it gives us a nice platform for taking some of these more ad hoc extensions that you might have seen in Rocketship and turning them into like first, or at least supported features with like a defined API as part of Chisel. Some simple examples that are already there, but there are more coming, are clock gates. That's obviously a really important thing. Plus-arg readers, or plus-args, which are obviously useful in simulation. A way to check if something is X, which I'll just kind of leave at that. But a really big one that has already been implemented now is very exciting, which is temporal properties. So this is something people have asked for years. You might be thinking of this as SVA or system Verilog assertions, but people want the ability to describe more complicated temporal properties and not just immediate like A equals B. They want, well, I'll show you. They want that A implies B followed by C, right? And things like that. This is like the industry standard in verification, especially in formal verification. And so this API is built on top of those intrinsics, which allows it to happen faster. Eventually, we will turn these into first-class IR features, but the intrinsics give us kind of a way to hoist ourselves to that level much faster. This took one of my colleagues only a few weeks to implement on his own, maybe like 2 or 3 weeks. And so there's some tweaks that will probably be likely before we release 6.0, but this code is code that I ran yesterday. It works. You can generate your system Verilog assertions. It's very exciting. Another thing that I originally had 7 slides on this, but in the interest of time, I turned it into 1. I could talk about these types of semantics all day. It would bore everyone in this room. So I'll just kind of gloss over it. But connection semantics in Chisel in the past were way too permissive. In Chisel 2 years ago, it didn't care if the types matched at all. Nominal typing, meaning if you name a type, like this is a class named foo, then it didn't require that you could only connect foos to foos. Structural typing is like, are the actual fields of this type the same? It didn't require that either. And it didn't require the widths to match. It didn't require much. It just kind of did something. Chisel 3 made this a bit stricter. The fields had to match. But being that rigid is also problematic because if you have 2 types you want to connect and their fields match 99%, but one doesn't match, what do? That rigidity then causes you to blast out the connection and you've thrown away the safety anyway. So not actually helpful. And it also would still just happily deal with mismatched widths, which is not great. So we have new operators starting in Chisel 3.6 that check the nominal types must match, but you can easily opt out. It checks that the structural types, the fields match if you don't have matching nominal types, but you can waive those fields, and it checks that the widths must match, but you can, the term is squeeze, that's the API, but you can say, yes, this width doesn't need to match, but all the rest do. So that gives you the rigidity of when you connect things, it checks everything for you. But if you have a need to waive just one small part of it, you can do that. And it's really useful. It's been very successful for us at Sci5 at least. And we're planning to migrate the older operators in newer versions. All right, so that was everything that is already there. You can go use Chisel 6.0.0 M2, and that's all there. So what's up next? Well, I'm going to immediately start with one that's only sort of next because it's actually already there, but is aggregate preservation. And this is supported by FurTool. It works well for Vex. I'm marking it next because there's some complexity with how this works for bundles, and so it's currently off by default, but you can turn it on yourself and use it. And it also can impact QOR. This may come as a big surprise, but even these expensive proprietary tools don't always do as good of a job as you think. And the optimizations we run in FurTool on, well, let me show you the current lowered output. The optimizations we run on the scalarized output actually does improve the QOR you get out. I think we need to do more of a study on that, so I'm going to kind of hand wave a bit, but we have noticed that when you turn this on, you can get worse QOR. That being said, this example just shows something very simple. We've got an input vector, an index, and an output, and we're just dynamically indexing it, right? Common like array access, if you will. And as any Chisel users know, Chisel will scalarize that vector into individual pieces. And then, of course, this output from FurTool is already better than what SFC used to do. It used to kind of unroll muxes, which looked really ugly, even though it gave you a good result. People didn't like how it looked. FurTool is doing something better. But now if you turn on aggregate preservation, you can have your Vec as a system Verilog array in your ports, and it looks like what you would expect at the system Verilog level. I talked a bit about connections, and so there's other aspects of width safety that have been weaker than they should be in Chisel in the past. These are kind of famous warts that we're fixing. And so here's an example where I have a dynamic bit selection. So I have an 8-bit value, and I can select a bit using 4 bits or 2 bits, which are wrong. You only need 3 bits. And so in both of those cases, you'll get a warning that your width is too large or too small. And so we're rolling out more of these warnings in order to kind of tighten up the semantics around widths. Now, one really big problem with rolling out new warnings is for certain things, you might get a lot of them. And so this is a little bit of a scary example but the real numbers that I have internally are over 100 for some of these new warnings, like 100 warnings. And I talked about those great new warnings where you get the warning, the line, and the caret. So that's 3 lines per warning, right? So if you had 241 warnings, that's 700 lines of warnings, right? Which is almost worthless because, you're not going to fix this many things in one go. And you're going to just try to make forward progress. And then one of your coworkers is going to add a new one and no one's going to notice, right? And that's like a huge problem. You want warnings as errors, but if you have hundreds of them, you can't, like in GCC, you can't turn on warnings as errors when you have too many warnings, right? And it makes it really difficult to kind of manage that. So there's a feature in Scala itself that we're basically deriving a similar feature in Chisel, where you can have more focused warning configuration. This is currently an open PR, so the actual syntax is not fully specified yet. But what I'm getting at here is you can pick by ID, you can filter with a glob based on source file because of those new source locators. And then you can provide an action, this S meaning silent or suppress, a W for keeping it as a warning, and E for erroring. So what I've done here is assuming some warning ID 3, which I haven't assigned them yet, so this is made up, but this would allow you to filter all warnings of this category in this directory and silence them, and anything else is an error. And so this gives you nice flexibility where you can say, okay, I'm going to fix, I have 1,000 Scala files in my code base. I'm going to fix them for these 50 and turn it on as errors in those files and then just keep the rest. And so this allows you to migrate your code in a much more reasonable way. Another thing that's pretty exciting, and this is very much half-baked, so don't hold me to this syntax, are groups. This is a way of kind of grouping non-functional statements. You can think about this as like the traditional methodology of having a module that you bind in for your verification. And so these groups can then be optionally included in simulation, and a really nice feature of these groups as they're currently specified is they allow nesting and hierarchical access. So if any of you have done a more traditional system Verilog verification methodology where you put your assertions in a module and you bind it in, it is outside of the Verilog spec to have a nested bind, to have a bind that you bind into your bind. That's not allowed. It is allowed by Verilator in at least one proprietary tool, but rejected by the other one. And so, one nice thing about a compiler is that we can support that API and then lower it to something that works according to the Verilog spec. And so, and also, if you have like some hierarchy of modules, say here I have foo instantiating bar, in System Verilog, if you have 2 bind modules that you're binding into each of those, you can't talk across those modules. There's no way to communicate. Like you have this sideband collateral and the sideband collateral can't talk. Well, with these groups, it can. Okay, I'm almost done, so mostly okay timing. And so here I'm showing that you can have your design, you can have this optional group that I've called assertions, and you can do something with it. It doesn't really matter what the logic is. I'm delaying it by a cycle. And then you can, in the parent module, you can access that information that is defined here in the group in the child, and then you can put an assertion on it. And so this allows you to do really powerful verification in a way that's you can keep separate from the system Verilog you emit, which is really important for traditional flows for synthesis or verification. And it generates things such that it just automatically handles the fact that some of these constructs are not directly supported by Verilog, and so you can lower them to cross-module references and stuff. And another thing that I'll just kind of gloss over, because this is very much a work in progress, are properties, which is a new type system for information about the generated hardware. This is for a lot of things like, what is the latency of your interconnect? That may be a derived parameter based on how the generator works, or your address map. And these are things that you need for software, verification, physical design, whatever. And then finally, the native dependency on Virtual has made Chisel installation a bit more annoying. So we have some work that's almost finished where we will co-distribute Virtual with Chisel such that this is kind of obvious, but it's, distributing Scala things has a very convenient process for it. And then distributing native binaries has its own entirely different process. And so trying to mix those worlds can be complicated. So we've come up with a system to make them distribute together. And there's also now Windows binaries for my Windows users. And if you have other platforms that we're not currently supporting, please come help us out. All of this is open source on GitHub. And that's it. So please check out our website. It has links to the repo, and check out Circuit's website as well. Thank you.
All right, thank you so much, Dan. Thank you for a great talk. Are there any questions here in the audience or online?
Hey, I played with Chisel a while ago, probably 3-4 years ago, so maybe my question is outdated. But yeah, I'm working on formal verification, and one problem I found with these generated designs, when I find a bug, I only get the counter example on a generated whatever system Verilog. Is there any plan, is any big vendor actually trying to back annotate that information such that I can basically debug in the Chisel, which would be way more convenient?
I don't know how much I can say at this point, but there are ongoing discussions on that. So the simple answer is today you have the source locator. So if you find an issue with the signal, it's pretty easy to see what it comes from. But more integrated support with the tools, there are discussions. That's all I can say.
Thanks.
Are there other questions here in the audience or online?
Hi. Could you clarify the new naming scheme? So I see that 3.6.0 is remapped to 6.0.0, but what about, you mentioned 3.5.2 and 3.5.6. So what are those mapped to?
Yeah, so to clarify, 3.6 is not remapped. Like 3.6.0 was a major release. The next major release is 5.0.0. So that is a version that comes after 3.6. And the version that comes after 5.0 is 6.0. Okay,
so there's no
remapping. It's just that.
Is 5.0.0 still upcoming?
5.0.0 is out.
Okay.
And 6.0.0 is coming soon. And then 5.1 will also come out, but that's, kind of a whatever back patches.
Thanks.
Well, it's not remapping. It's just new numbering for future versions. And this is a problem with animations. It takes forever to go back. Oh, I went too far. There we go. So 3.6 is followed by 5 is followed by 6. And I'll make sure that this is clarified on the website as well.
With the whole MLIR move, can you somewhat say how difficult it was for you to change like the whole interface between Scala and MLIR?
Yeah, so fortunately, Fertile already had a spec. And so implementing the spec was pretty easy. As with most things, that first 90% took almost no time. And then I talked about all those custom extensions that we had. That was by far the hardest part. And that's part of the motivation for why we're just like, we're not doing it that way anymore. If you want, like a lot of these features you're seeing are more principled and specified versions of things that we at Sci5 kind of already had in ad hoc forms. And the reason that they weren't public was not because they were secret sauce, but because the implementation was bad. And you don't want other people relying on your bad code because then you have to fix it. And so a lot of the effort, the hard part has been, okay, the basic spec that supports hardware is like really easy. All the other stuff took forever. And so that's what these new features are about, are trying to make that work better and be specified in a first-class feature.
I was just wondering, does your Scala go to some intermediate representation I could generate from other languages?
Yes, so Fertile. And Fertile is our intermediate representation. There is a Fertile spec on the Chips Alliance repo. And whereas in the past, like all these custom extensions via annotations were like not in the spec because they were custom extensions, all these features I'm talking about are in the Fertile spec. So if you want to see, it was basically stagnant for like 3 years and it is evolving pretty fast now. So I recommend checking it out and you can totally generate it from whatever.
Thank you so much for a great talk, John. Got to be quick. Try to keep it on schedule. Here, hang on.
Sorry. Going back to the follow-up the formal discussion, just clarification, when you're talking formal and your discussions with major vendors, are you talking about logical equivalence or assertion-based formal?
For integration with tools, I'm just talking about discussions about how it might be possible to remap from Verilog back to Chisel. I don't have any specifics on what kind of tools there.
Thank you. Thank you much again, Jack, for a great presentation. Appreciate it.
Thank you, everyone.
All right. So our next speaker will be Mikhail Mosov, and he is a senior staff engineer with Intel Labs. He's working in hardware design and verification automation tools. He is a maintainer of the Intel compiler for System C and participates in System C work group. He has a PhD in computer science. So, Mikhail, the floor is yours.
Hello, can you hear me?
Yes, and we see you as well.
Okay, great. Let me share my screen. Oops. 1 second. Okay, can you see my presentation?
Yes.
Okay, so my talk today is about a single source library for digital design and virtual prototyping. Let me start with a problem statement. So normally in conventional hardware design flow, beside hardware design RTL sources, there are some another models like pre-silicon models used for architecture exploration or performance evaluation, some virtual prototyping models used for firmware or software development. And usually these models are developed independently from hardware RTL, and that leads to extra resources for multiple models and some problems like parallel modifications of the model and checking equivalence of this model and RTL design. So to cope all these problems, we propose a single source design flow which use the same System C source code for hardware design, for pre-silicon models, and for virtual platform models. So initially we have some architecture specification, and a designer creates a System C design using single source library. This System C design can be translated into synthesizable System Verilog with Intel compiler for System C, which is open source tool. And this System Verilog is synthesizable, and finally silicon can be created from it. To be used in pre-silicon models and virtual models, the System C design just taken as a C++ source and compiled with a normal C++ compiler. So let me introduce the single source library. It's a library of high-level communication channels which supports two modes. The first mode is cycle accurate, which is a normal cycle accurate mode with clock, reset, and all the details in simulation. And second mode is a fast simulation mode. There is no clock, no reset, and all the simulation is request or data-driven. That leads to no extra process activation until there is really the process functionality is really needed. Besides the increasing simulation speed, using this library forces some new design style. So instead of process synchronization with individual signals or register or ports, there is high-level channels that reduce total line of codes and also reduce the risk of some synchronization errors. So the library includes a number of channels. Initiator and targets are used in pair and allows to communicate between two processes. There are also multi-initiator and multi-target intended to connect multiple processes. Also, there is signal input, output, output ports, very similar to System C ports. Register and FIFA could be used as convenient buffers to store some data in a process. There are also some additional channels which are not open sourced yet, so I skipped detailed description of them. Each of the channels support two modes, cycle accurate mode and fast simulation mode, and each of the channel implements some interfaces, for example, CT-put interface, CT-get interface, and others. These interfaces looks very similar to TLM 1.0 interfaces. Let's briefly discuss the interface details. So put interface allows a process to put some request or some data into a channel, and there is a ready function to know that the channel is really ready to the next request. So of course channel could be reset and cleared, and there are non-blocking and main blocking put function to be used in method and thread process. Get interface looks very similar, but instead of ready, there is a request function to know if there is a request in the channel. Reset get, clear get also used in reset section or to clear the request in the channel. And it's possible to pick or get the request in blocking and non-blocking and main blocking style. So let's discuss a typical use cases. As I said, initiator and target used in pair to connect two processes. One process put some data into initiator, process in module 1. Process in module 2 get some data from the target, and of course this is the same data which is sent by initiator to target. FIFO can be used as convenient buffer just to store a number of data chunks in it. So signal input-output ports can be used as normal signal and input-output ports of System C. But FIFO also can be used as convenient inter-process communication mechanism between two processes inside of one module. Also, there are on-die ports. It's a base port for implementation of AMBA port, master and subordinate port, or OCP port or other ports. There is some memory wrapper to instantiate a memory like SRAM, RF, ROM inside of the design. And also some register is a special channel which is used to introduce state for stateless method process in System C. So let me give a little bit deeper into initiator and target. So they allow us to create combinational connection and buffered connection. So combinational connection are used when target process is always ready to get request. In this case, we don't need any back pressure, just need to have some request and request data. Buffered connection is used when target process can be not ready sometimes. And in this case, data is stored in some internal register. Also, there are optional register to introduce a pipeline just to achieve required performance, and optional FIFO just to have a convenient buffer inside of target. So there is a very simple piece of code, a System C code, with module A, module B. In module A, we have initiator and random process which generates some random numbers and put random numbers into the initiator. In module B, we have target, and this target is used in check procs. This check procs gets a request from the target, checks if it equals to 42, it asserts the interrupt. So here, random process is thread process, so there is a reset section where initiator is reset, and while loop where all the functionality is implemented. So here you can see may block and put. So that means if initiator is ready, there is no delay, but if it's not ready, there is a wait until it's ready inside of this main block input function. So in checkprod, there is also reset get, which is just initialized target outputs and the logic. So in top module, both of modules are instantiated, and initiator just bound to the target. Of course, target also could be bound to initiator. The next channel is FIFA, which could be used in three cases. So first of all, it's for two processes communication. Second is as a buffer for one process, and the third one is using inside of the target as an internal buffer. Let me give you a simple example. Here in this example, we have two processes, producer and consumer. And producer, both of the processes are combinational processes, method processes. And there is one FIFA which is used to communicate between these two processes. As you can see, size of the FIFA is 2, so we can store two requests in this FIFA. So in producer, we do reset put. And if there is some condition and FIFA is ready, we produce next value and put into the FIFA. And in consumer process, it's also combinational. We do reset get and try to get value. And if there is a real request, this get method return true. In this case, we consume this value, do something useful for it. So, as I said, signals and input-output ports are also required for the designs which are using single source library. That's because a single is very simple and could be used, could be written by one process, but read by multiple processes. FIFA channel cannot be used in such a scenario. So for this special case, signal and input-output ports are also included, were also included into the library. So a register, as I said, it used to extend a method process, combinational process with state. So normally when we need some asynchronous processing, so means need to take and process some input data without latency, we are using method process. And if we need to have state for this process, we additionally use a thread process. To avoid extra process, we just add the register. In our case, it's a counter. And this counter here is used to count number of input requests taken from the target. So counter, here we call reset for the counter, and just increment counter for each request taken from the target. Of course, there could be a number of register used in one method process. So systemc has a SC port, which has a specialization for signal, SC in and SC out. And SC port also could be used for all the channels I mentioned before. So here is an example, SC port for a target and initiator. So here we have a child module with target and initiator, and we would like to promote this target and initiator to parent module to be connected to some initiator and target in the test bench. So to avoid some replication of initiator target, we just have a C port, which is internally implemented as a pointer, and bound a C port to real initiator and target inside of the child module. Really, there are lots of features. I avoid to discuss every feature, just mention one of them. C++ structures or classes could be used as a channel payload for signal, for initiator, for target, for FIFA. to support that. So to support that, we need to satisfy some requirements from systemc. First of all, such structure should have a default constructor and comparison operator. Also, it should have operator less for output stream and sctrace. As soon as we provide all these operators, we can use it inside of, for example, in our case, inside of the target. And we can use it as a normal payload. There is no restriction here. So let me compare this single source library with existing solutions. There is a Matchlib open source library from NVIDIA. And it's a really good library with lots of channels. Also, it has initiator, targets, bypass, and other channels. And it's really good. The main difference is that this library is intended to be used with Catapult C HLS tool and only with it. And this tool is a commercial one. Our library is can be used together with Intel compiler for systemc, which is open sourced. Also, this library, Matchlib, has some limitation. It can be used in clock threads only. And because of that, a latency of every module could be 1 or more. So we cannot create pure combinational module. In our case, we don't like to have such a limitation, and our channels can be used in method process and thread process. And we can create a module with a latency 0. Okay, experiments. This single source library has been created about half of years ago and open sourced just a few months ago. But we already have about 100 designs with these channels, and currently we have one big internal project at Intel, which is using this single source library. Here I just provide a few examples to show how using the single source library can reduce the total number of lines of codes, and what is the simulation speed up for a fast simulation mode in comparison with cycle accurate mode. So concluding my presentation, single source library provide communication channels that could be used for cycle accurate mode and fast simulation mode for a virtual platform and some pre-silicon models. And using this single source library, our experiment shows that it increases design efficiency and design time can be reduced about 2 times. Single source library channels are synthesizable for compiler for systemc and distributed as a part of this compiler. And you can find the library and this tool at Chipalyan's GitHub repo, which is showed here. So thank you for your attention. Any questions?
Thank you, Mikhail. Any questions here in the audience? Are there any questions online? I think we do have it. Say, do you have a question?
Hello.
Go ahead.
Yeah, actually, I missed the most part of this webinar. Would I be able to, get the access, from Linux Foundation afterwards or something like that?
Yes, the recording will be made available, will be posted on our website, and also work on getting the presentations.
Okay.
Go ahead. Mikhail, this is Rob. I did have one question. I'm just curious, how many developers work on this, either at Intel or in the open source community?
So really, inside of Intel, we have only 2 developers. Previously, we had more, but community helps a lot, and there are lots of bugs and feedbacks and feature requests from community. Some examples provided by community. So yeah, it's really big help.
No, that's great. And I don't know if you can comment. I'm just curious, does Intel use this for all of its design work, or do they use different design entry choices?
No, it's quite a new technology, and of course, I'm promoting this technology inside of and outside of Intel. So yes, we have multiple projects with the Intel compiler of systemc and number of silicons already alive, developed with Intel compiler for systemc. But most of the project, of course, some big cores, some other project, they do not use this technology.
That's great. Thank you so much again for your talk. I appreciate it. Oh, there was another question? Sorry.
In the chat. Yeah, there's a question in the chat. Is the generated Verilog output Yosys compatible?
Excuse me, which compatible? Compatible with what?
Is a generated Verilog Yosys compatible? Yosys is an open source synthesis tool.
Oh, Yosys. Okay, got it. Yeah, it's Yosys compatible. I had experiments with Sherlock and passed about 1,000 unit tests generated by Intel compiler for systemc through Sherlock, and all the tests passed after some minor fixes. So yes, generally you can use it with Yosys.
Thank you. All right. Thank you, Mick. I appreciate your talk.
Thank you.
All right. Our last speaker this morning is Mehdi Saligane from University of Michigan. He's a researcher there and works actively in the analog community and in particular OpenFASOC. And I've had the pleasure of working with Mehdi for over 2+ years now, I guess, right? So chairing the Mehdi chairs, our analog work group. So thank you for making the time to come.
Thank you. Can you help me? Once again. Are you? I just don't see my screen there. So, or maybe.
Are you?
How do I extend my?
Are you called into the meeting?
Yes.
You are. So you should be able to.
But how do I share it? Or
you should share it from the meeting.
Oh, okay.
Go to the meet where the meet. Yeah, there you are, and then that button right there.
But can I extend my screen on there?
It'll do that.
Okay. Okay. This one here.
That one. And hit share.
Just make sure your mic and camera are turned on.
Make sure your mic and camera are turned off on your.
Yeah. Okay.
You are on.
Hi. Thanks for the intro, Rob. My talk is about building confidence in OpenIC design using OpenFASOC. So there are so many reasons why open design is a must today. We need more chips, which means more open source EDA software, more collaboration, and a drastic shift in our mindset as designers or hardware designers. The way to do this, obviously, is by lowering costs and barrier to chip design. But the current status quo in the chip industry is limiting, and we have to go through a bit of history to understand why. So let's take an example in software development in the 90s. This is what it looked like. We had in-house compilers, lots of incompatibilities, and a lack of standardization, so everything was always dependent. Relics of the 90s is a common way to refer to these absurd issues we had back then, and there's a whole bunch of funny blogs about it. But more seriously, this reminds us of something today. To me, it definitely looks like IC design today, where of course we have access to much more computing power. But in general, the semiconductor companies have in-house tools. Our tool chain lack interoperability and require tedious effort to exchange data formats. And most importantly, tools are very buggy and support is lacking. As a matter of fact, I like to survey our new students and ask them to describe their tape-out experience, usually in an older node using one word. So the result isn't great. About half of them is negative, and the other third is neutral. Now, imagine if you ask new generations of students with an already software-oriented mindset who might have less motivation to sit and debug why their tool is crashing after a tedious place and route run without actually being able to look into the source code. I'm not sure if this may still make chip design as exciting, and the usual comment is we are fighting the tool instead of learning chip design. So at one of the major tech companies where they have an army of software engineers, like Google here, the ratio to hardware engineers is very imbalanced, which is actually very symptomatic of the overall US workforce situation, and also new students' career choices. Based on the Career Explorer website, we have about 70,000 hardware engineers in the United States, and which is growing by 5% in a decade, while we have 10 times more software engineers, which is supposed to grow by 30% in the same time span. So the idea here is to find ways of turning software engineers into hardware-friendly engineers. To give you a more tangible example of my idea here, last summer, Ali, who's an undergrad student, who's 19 years old, undergrad student from computer engineering department, so he's more software friendly. He reached out and he wanted to work on to do some work around OpenFA SOC, and he ended up winning at the ISSCC Code a Chip Notebook competition and presented his work on OpenFA SOC Digital LDO. And the reason he was able to do that is because he was working with software rather than working with transistors. That's a great demonstration of having more software-minded students to do hardware and software. So at software companies, development is within hours, which means deployment of new products could be done in weeks, while in IC design, it is well accepted to talk about months and years during project planning. And I'm not even mentioning the risk and costs here. Now, of course, there are time constants in chip fabrication that are hard to change. But looking back at my comparison to software in the 90s, there's definitely room for improvement to our methodologies and practices in hardware. In fact, if we talk to our software colleagues and even smaller community of EDA friends, it sounds like hardware development is broken. That's how they feel about it. And is this the case, though? The answer is no. We still make very complicated chips, but can we do better? Yes, and it is about time to fight in windmills and democratize chip design. So this is my last slide for my motivation here, but another angle is cost, right? Chips are very expensive to make. What we really need to understand here is when it comes to fabricating a new chip, the cost of building up a new integrated circuit from scratch at the wafer level can be very high. Licensing IP is expensive, paying for custom designs and EDA software can be very costly, and tape-out masks can vary widely from a few thousands to millions of dollars. This year at the ISSCC plenary session, it was discussed that it is required about 18 times to support a design from 65 nanometer to a 5 nanometer node. And to build a design at 5 nanometer, it costs about $500 million, which is crazy when you think about it. So in 2020, with my co-author here, Tim Ansel, we published this work about enabling open design with the release of the open source PDK, as you may have heard. And our work on EDS software such as OpenRoad, the stage was set to develop ways of designing and build an open source ecosystem. On my side, I started working on the open source corollary of FASOC that we call now OpenFASOC. So in summary, FASOC is a DARPA program, part of IDEA. It is a multi-university and effort led by the University of Michigan in partnership with ARM. FASOC specializes in autonomous SoC synthesis, which include all the building blocks such as analog generators, memories, and cores. So over the course of the program, we taped out a good number of chips in GF12, CSM65, and we demonstrated all of this in the ARI summits. And the past 4 years, I have been involved in new initiatives that aims to enable chip design. It started with the IDEA program, FASOC and OpenRoad. And then thanks to Skywater and Google and the open source PDK initiative, where I work closely with these guys and along with partners like NIST, we started rethinking some of the hardware design methodologies that could potentially revolutionize how chip design is done. Now that the IDEA program is over, we are still alive thanks to funding industry partners such as Google, KLA, and NIST. And thanks to the Open MPW program and open source tools, our framework evolved in many ways. I'll go through that in my presentation here. But we were able to crank out a large number of chips over these past 3 years. So these are some of the projects we've been working on. The reason mentioned in OpenFASOC here is that it allowed us to crank out these chips, which will build confidence through silicon results. So some of the projects we've been working on are usually just demonstrators in open source community, like sensors and DLDOs, but also the NIST nanofabrication accelerator. We're taping out a huge chip this week and next week. We also started working on cryo-CMOS. We started working with Fitbit on rapid prototyping for the wearables, and finally we were funded through SRC for hardware security and make the first open source implementation of the OpenTitan or an open. I'll go through that later in this presentation. So the release of the Skywater PDK has been a huge success and enabler. It is activating innovation and collaboration in many ways for different semiconductor communities. And as such, NIST and the nanofabrication community are extensively benefiting from this. And now we are building a career wafer with integrated CMOS circuits that allow physicists and nanofabrication engineers such as Dr. Brian Hoskins and his team to monolithically integrate and characterize emerging novel memory devices. This is exciting and unprecedented for designers to create new circuits to complement the nanofab research work. We are currently building an automated platform using our OpenFASOC framework to enable this across different nodes and cater to different specifications defined by the nanofabrication researcher. We are also putting together proposals with other partners to seek funding for this type of effort to NSF. We have achieved some initial results, including the release of the cryo models in Skywater 130. Together with partners such as CoolCAD and NIST, we have developed a test style to enhance these models. Thanks to the assistance from Dr. Akin from CoolCAD, we have also created more complex circuits for the nanofab accelerator capable of operating at 4 Kelvin. One of the most interesting designs we have built was a GF12 nanometer, which consists of a recursive SAR DC-DC converter based power management units generated using our automated framework. The fabricated chip was tested by NIST across a wide temperature range from 400 Kelvin down to 20 Kelvin, and the setup is shown on the left. Before getting to this point, we had to build confidence in these tools, as I said, and our framework heavily used OpenOverRoad, which is an open source tool. And since we were part of the team, we were able to crank out this chip here, which consists of 64 temp sensor array in the first MPW program. The curves here are silicon results we have shown previously in the CHIPS Alliance meetings. Similarly, in MPW2, we have made an SoC with an array of digital LDOs for different load currents. We can trade off settling time, output voltage ripple, efficiency, and even overshoots and undershoots. This type of generators combined with the usage of cloud infrastructure provided by Google, we are enabling data-based optimization and hoping to see more of this work using programmatic layout approaches using GDIS Factory, for instance. And as part of the IDEA program, we were able to use the GF12 shuttle to create prototypes using open tools. Our team successfully designed the first version of the OpenTitan root of trust, which included temp sensors that we developed using OpenFASOC. We also made the Bluetooth transmitter using an ADPLL, which uses the FASOC framework. Back to the nanofabrication accelerator program, we have put some test apparatus on a test chip, on a silicon chip, which will be used as a career wafer for new nanofabrication or nano device fabrication. This leads to improved measurement quality and test due to the reduced parasitics. We also have contributed to 4 shuttles already. Each had novel circuits. And my understanding, based on information from my colleagues at NIST, this would have required a long time to just design one of these test chips. Next was the Fitbit team, who reached out and started a collaboration with my group to help with rapid prototyping and accelerating their custom design process. They typically utilize off-the-shelf components and assemble them on their workbench. However, occasionally they may be missing some of the components with particular specifications. So OpenFASoc was a great fit here, and we taped out already 2 chips in GF180 and SkyWater 130, which consists of analog front ends that will be used in their prototype signal chain. Finally, Intel has provided us as well with their 16-nanometer shuttle, where we used it to build 3 fairly complicated test chips. One of them is the complete OpenTitan root of trust with security blocks, noise injection circuits. I'll go through that in some of my slides next. And then we did a tape out on 1st November 2022, and we did another one a month ago, which consists of a 2.8 giga sample per second time interleaved ADC. So yeah, so now I'd like to discuss this, the OpenTitan work we're making and all the peripherals we're building around it. And this work is funded through SRC. So my group was funded through SRC to implement an open root of trust using fully open and open flow that is transparent and auditable. Since OpenTitan is on GitHub, it was logical to adopt it and include our analog peripherals, such as the 2 random number generators and PMUs. To make the root of trust diagram on the left fully auditable and transparent, we propose to use our expertise in the open source EDA and IC design combined with the OpenFASoc framework. We have developed multiple silicon validated IPs before, and we plan to extend this work here to add the necessary building blocks for our root of trust, such as the secure PMU and the RM-based TRNG. So I'll go through that in the next slide. So we are proposing different countermeasures measures to mitigate side channel attacks, such as voltage domain stacking, which I believe could minimize the power signature of our AES accelerator. We are also developing a new secure and programmable PMU, which underscore the flexibility and broad applicability of the OpenFASoc generator approach. The PMU generator include power obfuscation circuits for side channel attack resilience, and include voltage regulation and noise and a novel noise injection technique. So our generator approach here is to expand our OpenFASoc style generator approach to security primitives such as the RM-based TRNGs. To perform the power obfuscation and reduction, the whole system is partitioned in 2 power domains. The memory instance, such as the instruction, data, and boot memory, should be sitting at the higher voltage domain. Here it is around 2.4 to 1.2, while the computational logic is actually at a subthreshold voltage. Since the bottom voltage domain only contains glue digital logic, including the encryption blocks, we plan to use a voltage scaling to further improve the energy efficiency, as well as reduce the power signature during the AES block operation. In stacked voltage implementation, the current drawn by the memory is directly reused by the logic in the bottom voltage domain, ideally bypassing the voltage regulator. As a result, the reused current is not subjected to power conversion losses, therefore improving power delivery efficiency. 2 DC-DC converters based PMUs using our OpenFASoc framework are being implemented to provide the multiple power domains, and we expect that the 2 similar voltage swing would confuse the attacker and make DPA harder. The second countermeasure is the secure programmable PMU with noise injection structures. The top-level architecture consists of 6-stage converter and non-overlapping clock, digital DAC, and noise injection block, which will be implemented using OpenFASoc. And based on this, in our early stage exploration, we try to replicate the work in the previous slide. We use the pulse wave, making the RM cell go from reset to set and the read phase. So there isn't many technologies using RM, so this is mainly a research project, but we have other options using fully digital true random number generators, which we actually implemented in Intel 16 last tapeout. This is the November tapeout 2022. We already got the chips from Intel. They actually provided us with the socket and all, so this was great. And my student is building the PCB, so we can start the testing. In this test chip, we made a temp sensor, an array of temp sensors using an end-to-end flow, open flow. So that was great to see. And we're actually implementing special router in OpenRoad to be able to do some of the analog routing. The second tape out, which is actually the final version we're planning to do using OpenTitan. We have already a tape-in of this block here. We actually included 2 random number generators based on a ring oscillator, and the PMU and the PLL and so on. And all of this is using open source tools, which is really great, except for verification, where we don't have open tools yet at FinFET technology. This is the implementation. There's a PLL, as I said, and a TRNG. All of these are using OpenRoad for the implementation since they are digital friendly. On the next slide, I'd like to talk about our framework and how we're using Python to use OpenFA SOC here. So I like this slide here from Tim Ansel and Proppy here from Google. But the summary is make custom silicon easier to build at scale, just like software. Proppy has been doing a great job actually packaging all these tools with Antmicro and so on, so that we can build this tool easily on our tool chain and use them in notebooks and so on. OpenFA SOC here is actually mainly code, right? So it's actually very different than how circuit design works. So it's kind of confusing for hardware designers. But OpenFA SOC is actually auditable and transparent, no malicious or tampering with the generated designs can be done. We also are having regression tests, systematic metrics extraction, and dashboards. Finally, analog automation has been an issue for a long time, and it's really hard to say that analog automation is fixed now. But since we're working in the open now, we can still combine multiple expertise in the EDA, analog circuits, and software, so we can fix this problem. So we started exploring new ways of automation using GDS Factory and so on. Certain blocks such as auxiliary cells, which we use in our procedural generators, and on circuits like transimpedance amplifiers and other circuitry necessitate direct control over the layout and are not suitable for the cell-based approach that we usually use in OpenFA SOC. So this provides a time-limiting step with porting to new PDK. We want to automate as much as possible while keeping the generator agnostic, PDK agnostic. To address this, we are developing programmatic generators employing GDS Factory, which is developed here by Joaquin from Google X Photonics team. GDS Factory provides a framework for programmatically building layouts with object-oriented code. The main advantage of this is to keep cell software generation dependent on PDK. So PDK is, in our framework here is implemented as a Python class, including the layer stack, design rules, and the library of components such as pcells. The generators are now implemented as Python functions, which will return full layout stored in GDS Factory components. This function can accept arguments for automatic customization. Generators can also call other generators to produce a hierarchical design. The user interface with the generator is a Python package. The user can import their PDK package and the target generator. Then in one of the line of the code, they can actually create a full layout. With programmatic generators, we can actually achieve quick creation of layout from Python functions, enabling reuse across different designs with varying design parameters. And here we are automatically generating a current mirror and the comparator. The other work that is being done here, and thanks to Google Summer of Code this year, which allowed us to have 3 motivated students who are actively working on implementing features to enable automation and interfacing between tools. Mohit, who made this diagram here, is implementing front end of the line classes in OpenRoad. as well as a GDS writer and reader to help co-integrate with other tools such as GDS Factory. This is a really enablers for analog automation, since we can build our circuit within OpenNode rather than outside OpenNode. So now, regarding outreach, earlier this year, we were encouraged to submit a proposal to the US Embassy and Consulate in Japan to organize a workshop and to train the local high-tech labor force. And last month, we were notified that this proposal, which is built around OpenFA SOC, and which usually uses the Open PDK and notebooks and so on, was selected, and they are considering making it as a model for the next workshops and training in the Asian region. Now, next in my talk, I'll talk about activities that CHIPS Alliance is actually funding. This is our committee here, which is the SSCS, IEEE SSCS committee, which is chaired by Professor Boris Merman. And this is our roster here. It is open. We are always turning the members, so please reach out if you're interested in joining us. But CHIPS Alliance has helped us through Google and so on to fund some of these efforts here. So one of them is the Chipathon, which started in 2021, and we launched it with Professor Boris. We see students from underserved communities in the US and all over the world joining us in weekly meetings to learn how to do a tape out and get travel grants to flagship conferences such as ISSCC and so on. So the first edition was in 2021. We had about 11 submissions, tape out, more submissions, obviously. And as you can see, they are mainly from all over the place across the globe. The second version had more tape outs, so around 14. We had more elaborated circuitry there. And this is really great because it can generate IPs for CHIPS Alliance and our community. But in this year's Chipathon, we changed a bit the way we want to run it by making the teams propose new circuit ideas that could be used to build a lab on a chip. The reason we want to do that is because there's a lot of communities that doesn't have equipment, test equipment to test their chips or the open design. So having this lab on a chip would allow them to have oscilloscopes, macros that they can use to test their circuitry. The other things we started is and to funding to CHIPS Alliance, the Code a Chip competition, which we had the first version here at ISSCS 2023. We had about 7 winners from different places across the globe, and CHIPS Alliance has funded it here, as you can see on the picture. The next Code a Chip competition happened in VLSI 2023. We had 2 winners from University of Toronto, and one interesting thing is we started seeing analog circuitry combined with AI or machine learning to generate the circuits in a notebook, and that's thanks to the open design and the PDKs. This is the call for the Code a Chip competition. We'll have a next one in ISSCC 2024. Sorry, I didn't update this slide, but the plan is to continue this competition here in VLSI and ISSCC through funding from SSCS. The other thing we wanted to do is allow venues for publication, right? So open design is not as leading edge as closed design, so it is hard to publish in conferences like ISSCC and VLSI. So with our committee, we did the first session at ISCAS, which is around open source design, and we did a review of all the silicon results we had in MPW 1 and 2 and so on. So I chaired this session with my colleague, Priyanka Rana from Stanford, and we had a bunch of work from such as OpenRAM and so on. The other thing I wanted to mention here is we had an open source workshop at VLSI, which had about 180 attendees. That's unheard of. That's a record in VLSI in the circuit community, and it was great to see so many people in Japan join us in our workshop. And I think they are thinking about making this as a normal thing that happens every year. So thanks for your time, and please let me know if you have any questions.
Thank you so much, Mehdi. Any questions from here in the audience?
So with open, how do you pronounce it? OpenFASOC?
Yeah.
So with that, is that a program that like students and like grad students and stuff do, or if not, what kind of program is it? I don't really understand.
You mean like with the usage, or who's using it?
Both.
Okay, so this is a good question, right? So I'm running a research group, and I deal with a lot with students. So one thing we do, I'm trying to implement, is having more software student to hardware. And the way we do that is through abstraction. And OpenFASOC allows that to our firm, the cell-based approach. You can check the other talks in CHIPS Alliance that goes through that. I do want to repeat the same talk over again. But the idea is basically you identify some cells that are basically a block, and you don't have to, if you're a software person, you don't have to understand what's happening in terms of transistors. You can just reuse that block and build it with the whole topology. Now, regarding education, it's very good for the students to play with the code and generate, at the end of the day, a circuit that is simulatable and all. The other thing is we actually work with industry partners to create, or even government agencies to create real circuits. So OpenFASOC is being used to generate blocks that are working on silicon, and we prove that through our results. So we address both, I guess.
And thanks. Can I talk to you more about that afterwards? Sure. Thanks.
Other questions here in the audience? Are there any questions online?
Oh.
Can you click
or
I can go to it.
Oh, okay, I don't see the chat. Okay.
Can you see it? I can read it to you if you wish.
You plan to adapt or to design chiplet? So we have plans to make an open SerDes, and actually we just discussed it with TCAR yesterday, who was working at packaging. We have some students working on that and building everything from using open tools. Now, making a SerDes using open tools is not easy. But we're going with the baby steps and building a PLL and so on, like all the building blocks. And when we'll have it ready, I think we're going to use OpenFASOC and port it across technologies. So I think that's in our plans. Now it's taking time and resources.
Other questions? So I had one question. I always enjoy your talks and the work. Oops, we do have a question, but I'll ask my question first. But how, I talked a little bit about this last night, as you know. It seems that with the open source EDA, which is a great effort, and it's very similar to, what I experienced in my career in terms of developing internal tools within a large semiconductor company, right? It's always hard. The designers hate you, whatever. I mean, it goes on, and I won't go on and on. But, in terms of how are things going in terms of industrial adoption of the work that you are doing? Do you have anybody who is using this in industry right now, or is that still kind of a challenge?
Well, I think the closest we're getting is through Fitbit. They are using some of the work we're making. Now the KLA is also interested, and we're building a time interleaved ADC in Intel 16. And there isn't open tools in Intel 16, so the only thing we're using is actually Python scripts and OpenRoad, which is great already. But SRC is another example. It's an industry-driven thing, and they are interested in our two random number generators and PMUs. And NIST is the other option, right, with the nanofabrication accelerator. So I think this is a good adoption. Now, we need to disseminate this more, and if there's any interest, please let me know, because we have silicon results, and we've shown this across different designs. So it's not like
you've done great work in that regard.
Right.
So yeah, thank you. One question online here. Let's see here. Do you consider to cooperate with other foundries to provide more technology in this project?
I don't understand what means provide more technologies, but basically supporting new technologies like what Pragmatic is doing. That's definitely possible. And we ported FASOC or OpenFASOC to different nodes, so I don't see why that's not going to happen. The other thing is GDS Factory is actually a really great platform to create Python scripts to generate layouts. So now we're supporting both, and we're creating these designs that can support different technologies actually.
I was going to also just agree relative to the efforts that you're doing. I know Tim has championed as well about trying to make hardware design more software-like and approachable to people, right? In my time in this role and chatting with different government entities or regions of the U.S. or the world, right? It's like we have this global problem of getting people interested in engineering, and I think a lot of that has to do with making it approachable. And I was chatting with some folks from Germany last night, actually, and it's like, we don't want to start off by showing them, partial differential equations or, something like that where they run for the hills, so to speak, right?
That's a really good point, right? And I think one thing we're trying to address with OpenFASOC is abstraction. Because building generators requires expertise, right? Like you can't be a PLL guy and an ADC guy and so on, right? So you have to abstract some of these issues, and that's how we're building OpenFASOC, so people don't have to deal with some of the analog black magic, or basically.
All right. Well, thank you so much for an excellent presentation, Mehdi, and thanks to everyone for presenting today, and for everyone who attended both here in San Francisco at Google and also online. And thanks again to Google for hosting us here today. So appreciate it. We'll work on making the video available, and if the presenters could send me the slides, we will get them out there as well. So thank you again, everybody.
And lunch is available for you right here. You should not have to be escalated.